Welcome, everyone, to the AWS Container Day with Docker. In my head, I'm imagining everyone clapping and applauding, just like we all used to do when we were in person. And even though we can't be all together right now, that's the energy I'm definitely going to take into today. My name is Jeremiah Dooley, and I'm going to be your guide to the day's festivities. I'm going to try to keep us on track, and I'm going to spend a lot of time introducing the wonderful lineup of speakers that we have for you today. We'll talk again in a few minutes and take a look at what's going to happen and what we've got lined up for you. But let's get things started here. First up, please welcome Inbal Shani, the GM for all of the AWS native container products. Take it away, Inbal.
Good morning, good afternoon, and good evening, everyone. My name is Inbal Shani. I'm the General Manager of AWS Elastic Containers. Now, before we get started, I just wanted to say thank you so much for joining us today, and I wanted to welcome you all to AWS Containers Day. I also want to take the opportunity and say thank you to our partners in Dockers, and I hope that everyone were able to attend at least part of the DockerCon yesterday, since we really appreciate their partnership and the fact that they allow us to tag along into the DockerCon with our own event on AWS Containers Day. Now, at AWS, we're deeply committed to removing any undifferentiated heavy lifting for teams. And in 2020, we announced a relationship with Docker that supports that commitment. What developers love is the simplicity of Docker Compose and Desktop, and yet they haven't had a simple way to use Docker and deploy AWS from their local development environment. And now this is handled natively, so you can do that. With our collaboration, it allows developers to use Docker Compose and Docker Desktop to deploy application on Amazon ECS and on AWS Fargate. And it streamlined the process of deploying and managing containers in AWS from a local development environment while running Docker. We expect to build more with Docker, and we really will appreciate your input. We're customer obsessed. We care about the voice of the customer, so please ask. I'm super excited about the agenda today. I think you're really going to enjoy it. We have a great agenda, and that includes two very special guests. Our own AWS container hero, Casey Lee, the CTO of Gaggle, as well as Lokonda Willa, the principal technical evangelist at SUSE. We really appreciate their participation today, and I cannot wait for you to hear their stories. After that, we'll hear more about AWS App Partner from Clorinda and Yimnin, as well as from Adam and Nathan, and they will walk us through serverless containers and containers application. And I'll return at the end to talk a little bit about where we're headed next. Now, with that, I want to say thank you again for attending the day. Please enjoy the sessions. I hope you get to learn something new. And then I'll hand it back to Joe.
Thanks, Inbal. Like I said earlier, my name's Jeremiah, and my day job here at AWS is to be the manager of the amazing team of developer advocates who focus on native containers. You're going to hear from each of them today. All of them have content that they're presenting, and hopefully this will be the beginning for those of you who don't know them yet of the ability to interact with them, ask questions of them, and learn more about the container ecosystem. We've spent a lot of time in partnership with Docker and with our amazing AWS container heroes to put together some sessions that we think represent the best of what the Amazon native container ecosystem has to offer. And we're really excited to get to share that with you. What I wanted to do real quick before we start off is to take a look at the agenda that Inbal just shared and maybe go a little bit deeper for you so you can get some insight into what these sessions are and what they're going to cover to find out if it's something that you're interested in. First up, we're going to have something specifically for those of you who are newer to the AWS ecosystem. And we're going to start off with Mesh, one of the developer advocates, and AWS hero Casey Lee, giving you an overview of ECS, what it does, how it works, and how it's the perfect entry point into the rest of what AWS has to offer. After that, Luke, one of our amazing container heroes from South Africa, that I just got a chance to meet for the first time here recently as we were preparing for this event, is going to share his story, is going to give some insight into the container hero program, and then is going to dig into security principles that will give you some things to think about as you build with containers. At about 12:15, we're going to take a 15-minute break. We may stretch that out just a little bit for everyone, depending on how things go, but just so you have a chance to get up, stretch out, grab a new mug of coffee, and then we'll kick back off again at 12:30, where Claire and Yiming are going to talk about one of my personal favorite topics, which is scale. They have a fun demo as part of that, so hope you'll join in for that third presentation. And then after that, we've got another one of the developer advocates, Nathan Peck, and he's really going to dig into the things that developers care about when it comes to building with containers and cloud technologies. We're going to dig in a little bit deeper on a few of the things that he's discovered as he's gone through and done some testing. And the previews that we've gotten from this particular session so far have been pretty great. So we're hoping that you enjoy it. The last session of the day is going to be Adam Keller, and we're just going to turn everything up to 11. We're going to try to show you how to take your applications to the next level, and we're going to look at some of the advanced tools and techniques that can be leveraged alongside ECS. And then at the end, Inbal will come back for the end of the event and give us a sneak peek into what's next for the container space, where we're looking to take it, and her vision for what she wants to do, not just with ECS, but with all of the Amazon native container products. So pretty exciting. I'm excited about it. These are some new sessions that we've built specifically for you as part of this audience, and we're really looking forward to getting your feedback on it. Sound good? All right, I think we are just about ready to move into that first session, so let's get to the good stuff. Maish, Casey, take it away.
Welcome everybody to the AWS Container Day. Today we're going to be talking about ECS and how it's your entry point into the cloud. My name is Maish, and I'm joined today by Casey Lee. And Casey, will you please introduce yourself? Tell us a little bit about you.
Yeah, sure. Thanks, Maish. Casey Lee, I'm the CTO at Gaggle. I'm also a part of the AWS Hero Program. I love building things, love working with organizations, helping them achieve their potential through automation. Gaggle is an ed tech company. We build software that school districts use to help monitor the school-issued Google and Microsoft accounts, and we're helping identify students that might need help, either because they're being bullied or harassed, or maybe they're dealing with self-harm or suicide issues. We protect close to 6 million students in the U.S., and last school year, we were involved in saving the lives of over 1,400 students that were about to take their own lives. We were able to get them help right before they were able to go through that. So that's Gaggle. That's my role.
That must be really feel good, making a good impact. Well, awesome. Thank you very much. I also wanted to introduce myself. My name is Maish Seidel-Gesing. I'm a developer advocate with the ECS service team. We work very, very closely with the product managers and the product team, and also the ECS engineers, in order to make our products better based on the feedback we get from our AWS customers. And it's a constant conversation and workflow going between us in order to bring your feedback from our customers back into the products directly. So today we're going to do a couple of things. It'll have a common theme, of course. Of course, everyone all has to do something about containers. But today specifically is about how Casey's going to talk to us a bit about their journey in Gaggle, of how they went into AWS, and how they optimized the development workflow, amongst other things. But before we start, I just want to I know what ECS is, Casey, so can maybe you give us your interpretation of how you would explain ECS to a customer or to one of your engineers?
Sure. So you've got Docker running on your desktop, right? Your first step is, okay, cool, let me figure out how to get this application running in a Docker image, and then I can get it running locally. But then when you want to run that application somewhere else other than your laptop, that's when things get kind of tricky. You've got a lot of options. And ECS provides a managed service that provides that control plane for running that image that you created locally, running that image in a single copy of it or thousands of copies of that image, running it as containers up in region in AWS. So it provides a real easy way to take that image that you created through your build tools and run it at scale.
Awesome. I couldn't say it better myself. So tell me what your ECS environment looks like in Gaggle.
Okay, cool. First, let me set up a little bit about how we use ECS to understand the scope of data. So in the last school year, we ingested over 6 billion files and about the same, just over 5 million emails in the last school year. So we pull that content in, and then we use ECS to run tasks that analyze that content, look for any concerning content from these students, and then notify the school districts about that. That resulted in over 40 million items that humans had to look at. So that whole workflow of pulling the content in, scanning it, and then the workflows is running in ECS for us. So a lot of data, a lot of traffic, and of course that back to school August, September is very high traffic surge for us as everyone gets plugged back in and assignments are getting sent out and teachers are sending welcome emails. So the way that we use ECS, with ECS you have a couple options, right? You can either run ECS on EC2 instances. You can use Fargate for scheduling your tasks. You can also, with ECS Anywhere, run your tasks in your own data center. We primarily use EC2 for running our ECS workloads. At our peak, like that back to school time when emails are flying and files are being created, we see up to about 3,000 tasks running. So our tasks tend to be one-to-one, one container per task. So it's about 3,000 containers that we have running at peak during that back to school time. And we generally have two kind of patterns that we use with these ECS services. Either they're sitting behind an SQS queue, or they're sitting behind a application load balancer. So the stuff that's processing content tends to be more asynchronous batch type activity. And so we put an SQS queue in front of those, whereas the more interactive applications, we use an ALB in front of those. But that's kind of the high level there. I want to go into some depth of how we manage our clusters and stuff, but maybe let me pause. Any areas I can go deeper on with that?
So the question I'd like to ask you, I assume that you never started at that kind of scale. You started probably smaller. You didn't start with 3,000 tasks going from scratch from day one.
For sure. Yeah, that's good. So Gaggle's been around for 20 years, long before ECS was a thing, before AWS was a thing. And so these workloads would run on physical machines in a data center, and then were being moved over time up to AWS. As those workloads were moved up, auto scaling was an important part of how those systems were run up in AWS. So for our SQS-based services, we tend to do step scaling based on the number of messages visible in the queue. So if all of a sudden we see 5,000 messages in the queue, we see maybe a superintendent sent an email to all 40,000 students, we'd see a huge spike in work that needs to be processed. So we would use AWS step scaling to then scale out the number of tasks based on that. On the ALB side, we use target tracking scaling, where we target a specific CPU and then scale out or in the number of tasks based on how they're performing. But in that fortunately, the team took that approach when they started moving things to AWS, because then COVID hit, and
okay.
all of a sudden, what happened? All the students started doing school at home, and things like Google and Microsoft for doing classroom management became mandatory. It was no longer a nice to have. Well, we saw a 400% increase in traffic on our platform almost overnight. And fortunately, we were able to scale it very quickly. All of our ECS-based workloads just responded immediately to the load. Of course, we had a larger bill, but the service remained online, and we were able to continue to protect kids during all that.
Awesome. So I assume when you're talking about this kind of scale and We're talking about the fact that you have to manage not one cluster, not maybe two clusters, a number of different clusters for different environments, for different regions if you need to do for DR. And I assume you don't do this, what everybody likes to call ClickOps, by going through the console and doing this manually. So tell us a little bit about how you manage your clusters or these number of clusters at scale.
Sure. So we've got a lot of different services, ECS services, that are running in our AWS accounts. But then we have shared clusters. So we will create ECS clusters based on a characteristic of the type of application. So we have memory optimized clusters and CPU optimized clusters where the types of EC2 instances that we launch in that cluster are better suited for that workload. So we use R type instance family, instances from the R family versus instance from C family in the compute optimized clusters. So we have a few of these different clusters that match the type of application that's going to be running. And then those are shared clusters, which presents some challenges, which we can talk about in a bit. But we've got these shared clusters that the different teams will run their ECS services in. And then all of those instances we like to use Spot for keeping the cost down on our ECS clusters. And so we use Spot fleet requests to provision EC2 instances and then have them added to the appropriate ECS cluster. And then we use step scaling as well on scaling out or scaling in the number of EC2 instances. And we do that based on how much memory has been reserved. So this is where it gets kind of tricky, right? You're scaling the cluster itself based on task reservations in the cluster. So you're scaling out and in the number of EC2 instances. And then you're also scaling out in the number of tasks running on that cluster on a service by service basis. So both of those we use auto scaling for, and that helps us make sure that we're aligning the amount of compute resources we have with whatever the current demand is. For provisioning those clusters, we use CloudFormation and CDK for our production clusters. But we also had a challenge of, hey, our dev accounts, they also need clusters. And every developer's got their own AWS account now. So when a developer needs a cluster so that they can do local development of their ECS services, how do we provision those clusters? And for that, we leaned on AWS Service Catalog, which allows us to define CloudFormation templates and then share them out to the developer account. And so then they can self-service create their own ECS cluster and have the instances provisioned for them.
So I'm kind of hearing that you're making use of a lot of AWS services in order to make your day-to-day operations and your day-to-day work with all your developers and your production applications seamless without having to reinvent the wheel.
Yeah, that's right. Yeah, and all these things play very nicely together. The integration between AOBs or SQSQs and ECS services, or then ECS and things like CloudFormation and Service Catalog, all flows nicely.
So let me go back a tiny bit. When you started out moving into a container or microservices, I assume most you are using microservices. Otherwise, you can't really run these on containers and in ECS clusters. But ECS is not the only container scheduler or container orchestration system available today. There's also EKS or Kubernetes, whatever. On AWS, we have EKS. There's differences between the two. It'd be interesting to hear from your perspective, why did Gaggle choose ECS?
Gotcha. Yeah. So we've been building our applications on Java for a long time. So we have a long history of an investment in Java. And so that was an important part of this decision, right? We needed a way of running these existing Java apps in AWS. So first thing you obviously want to look at is EC2. Why not just provision EC2 instances and move the applications up there? We wanted a higher level of abstraction than just managing VMs. With managing VMs, you're having to deal with the operating system level. You're having to deal with managing AMIs and configuration management of those EC2 instances. And so we shied away from EC2 because we wanted something that was more managed. Why not Lambda, right? We could have said, hey, let's just go all in. But we tend to use Lambda for greenfield development for existing applications. There's not an easy path to take an existing app and get it running in a cost-efficient and scalable way in Lambda. And the other thing is, where we do use Lambda, we find that it tends to be more expensive for us with Java as the language, just because with Lambda you're paying for the memory footprint multiplied by the time you're using it, and these Java apps tend to use significantly more memory. So it's a little tricky there. EKS didn't exist at the time when we were making this choice, so it wasn't an option. Kubernetes was very bleeding edge at that point, and your only option was kind of roll your own on AWS, maybe using something like KubeSpray or something to set up EC2 instances, but it wasn't mature enough. And so ECS was the perfect fit. ECS allowed us to take existing applications, containerize them, and then hide away a lot of the complexity inside that image. And it gave us the right level of abstraction where we could still have some control over the EC2 instances themselves, like what instance family we chose. And it allowed us to use spot instances. But then it managed the scaling out and scaling in very nicely. Great integration with AOBs and SQS. And so it was kind of that sweet spot for us with our existing investment and our existing approach for running apps.
And I assume it's worked for you guys as well, correct?
Yeah, worked very well. There's things that we'd like to do better at. For example, capacity providers instead of spot fleet requests. That was a relatively recent addition, was the ability to use capacity providers. So there's things that we could continue to improve at, and we're researching those. But yeah, it's been great for us.
Awesome. There's of course new things which are coming out, new innovations, new ways to manage your capacity and manage your cost as well, which we're going to get into a little bit later. But I'm going to ask you a question at the end of the session about what's next for you guys, but we'll leave that for the end. But so it's I assume you're not the only person writing code. There's a number of engineers and developers. So the first thing which comes to mind when I think about people writing code is it's awesome, it works on my machine, and you just say you need something to get it to the cloud. There has to be some kind of process, or some CICD process. So I assume you are using a kind of a workflow or a pipeline of some sort. So why, and I've got a slide here in the background if you can bring it up as well. Why did you adopt CICD, I assume? Because of a number of those reasons. What was the catalyst from you for Gaggle?
Yeah, this is a fun one. So yes, we're using CI/CD pipelines for our applications. That's been a lot of investment in that in the last couple of years, and it goes back to why did we make that investment in CI/CD? So maybe let me cover that first. We were building great applications, and our customers loved what we were building for them, but it took a long time for us to get things out the door. We were seeing a lead time of about 47, 48 days for when we'd start work on something until when it would be seen in production. Our deployment frequency, we were only going to production a couple times a week as an entire organization. Across all of our teams, we were only getting to production 2 to 3 times a week. And so we dug into that and we said, why is that? Why does it take so long for us to get things into production? And so we looked at the state of things, and we were using CloudFormation. We had YAML or JSON embedded in the Git repos for the different applications. We're using an Atlassian product called Bamboo to build our software, build our images, and then manage the CloudFormation stacks. But the problem came down to what you see in this picture here, which is that there was only one staging account, one AWS account that was used for testing before things went to production. And so what that meant was there was a bottleneck. There was only one path for developers to validate the changes that they're making. And we found that the feedback loop was extremely long for developers. And so this is kind of what the process looked like. You see, what happened there was developers would create a branch, and then they would do local testing, but they could only do a very minimal amount of local testing because things like ECS or some of the dependencies, SQS, Dynamo, Kinesis, AOBs, these were all things, Lambdas, they were hard to run locally on our workstation. So a developer could do some unit testing maybe, but that was as far as they'd get. So then they would push up their changes to a branch and then move the ticket to the QA team. There was a separate QA team that would then pull the ticket, and then when they got around to it, would take your branch, build it, and then deploy it to the staging environment and then test it. Well, as you can imagine, you've now got this huge bottleneck where all changes are waiting in line for QA to take over the environment with your change and validate it. And so we saw these very long feedback times for developers. And so our first approach was, well, let's figure out how to fix that. Let's figure out how to make it so that developers can get faster feedback. And so
you kind of, I assume you went and evolved. So we'll go to explain to us how that actually happened.
Yeah. So we said, well, we need to remove this bottleneck. And so the first thing we did was we invested in AWS Control Tower. We said, let's give every developer their own account, right? If every dev has their own account, they're no longer bottlenecked waiting for the QA team to pull their ticket, pull their branch, and deploy it to the shared account. Great. Okay. So now every developer has their own AWS account, and they're able to deploy whatever they want. But that brought about the next problem for us. The next problem was that developers couldn't actually deploy anything into these accounts because Bamboo was doing all of the deployments previously. We couldn't convince Bamboo to now start deploying into each developer's account. So what did we do? We started investing in CDK at that point. We moved all of our applications into using CDK for deploying the applications. This was a big lift. We had copied over CloudFormation into all of these different repos. Each microservice had its own repo. Each repo had its own CloudFormation. But the CloudFormation was rather large. It included everything you needed to run an ECS service. So creating the service, the task definition, the auto-scaling rules, all of that, all the IAM roles was all in this rather large JSON file that was copied around from team to team. So we pulled all that out into a separate, we used Python for CDK. So we created a separate Python module that had reusable CDK constructs for how to do things like run an ECS service. And then the teams were then able to start using that instead of CloudFormation directly in their repo. They were creating CDK apps in their repo that referenced that reusable Python module with the CDK constructs. So now they were able to quickly deploy their applications locally, right? They're able to CDK deploy, and now in their own dev account, they're able to run their app. But there was another challenge that we hit. So great, I can CDK deploy my application, and I can deploy all the AWS resources I need, the SQS queues and the Dynamo tables and all that stuff. But what about dependencies between applications? And so we ran into this other challenge, which is if I deploy my app into my local account, I also need to deploy the other microservices that I'm dependent on. And CDK really doesn't have a good solution to that. So we wrote a small tool that we called CDK-R for recursive CDK, and it allows you to define dependencies between services and repos. And then, so now I run CDK-R deploy, and the first thing it does is it looks at a YAML file, sees all my dependencies, pulls down my dependencies, and then recursively runs CDK on those. And so now we've got this really great environment where a developer gets a brand new account, They git clone their microservice. They run CDKR deploy. It recursively deploys all their dependencies. Now, the first time takes 15 minutes or so, but now they've got everything they need to do their development, including their dependencies, running in their own AWS account. And we're able to see our cycle time, a measure of how long developers spend on something. Cycle time went from almost 30 days, how long devs would spend on a ticket, down to 3 days. And their throughput went from 3 to 8 a week is what developers were able to get through, just by giving them their own environment to work in and their own ability to work quickly and get fast feedback.
So I'm going to let you catch your breath for a second in the meantime. But anyway, this is awesome. And the fact that I assume this was not the Valhalla of getting all your applications deployed, because I can kind of identify kind of bottlenecks here inside your architecture, which maybe is the fact of everything has to go through one server and you have to compete with people pushing other changes into your workflow into Bamboo. So I assume you also understood that. And how did you deal with that?
Yep. Yeah. So this picture that you've got up here, we've got all of these developers with their own accounts, and they're able to do their own deployment and testing. And the developers are like, yeah, this is awesome. But guess who now is getting the pain? It's the QA team sitting there in the top right corner in green. Now they still only have one account, and they're still manually playing traffic cop, taking different branches and putting them in the test environment. So developers were moving quickly, but it now added all this pressure on QA. So that brings us to our next piece, which is this, where we said, great, let's create more accounts, right? Creating more developer accounts seemed to help.
Creating accounts doesn't actually cost money. The resources you use inside those accounts, of course, do, but doesn't cost creating an account.
Yeah, Control Tower makes it very easy, too easy to create new accounts. So we said, let's create new accounts for each team. So rather than having each product team having all relying on a shared AWS account, we gave each team their own account. That's what you see in the middle there in blue. Each team got their own AWS account where they could do their own integration testing before going to staging. And so now staging was a quick, you spend an hour in the staging account doing final validation before it goes to production. But any manual testing you need is in the team account. So now teams are able to operate independent of each other, and we weren't constrained. We disbanded the QA team and moved all of the QA resources into the actual product teams, so that moving away from that single shared bottleneck that we found. But the other thing we did, which you can see here on this picture, is we moved away from Bamboo and went all in with AWS Code Pipeline and Code Build. So now each repository had a pipeline created for it. The pipeline would build the Docker image, push it to ECR, and then assume a role into the Teams account and do a CDK deploy into the Teams account. And then if everything looks good, the pipeline would then do the same CDK deploy into staging and then finally into production. So now we have one pipeline tied to the trunk, tied to the main branch that is moving code through the various accounts without needing a single team to manage the coordination of all that.
Nice. But you still have, I think, I can still identify a bottleneck here, right? If I'm not, you have the staging account, or there's still going to be waiting times for everything to go into the same staging account. So of course, this is an evolving process, and I'm sure you're going to tell us how it went further.
Sure. So we that's where these pipelines came in. So now each team account has a set of pipelines, and the pipelines are all managed through CDK as well. So we didn't want teams having to go in and what did you say? I like that, ClickOps. We didn't want them ClickOps creating pipelines. So we created a CDK construct for what a good pipeline looks like that manages the build, the integration stage, the staging stage, and the production stage. All of that is baked into a single reusable construct that all the teams could then use. So now all the teams were able to quickly stand up these pipelines that that manage the deployments all the way through. And then the team started investing in test automation that they would run in the integration account. So now we're not spending a lot of time in that shared staging account. There's still a single shared staging account that still exists. But the idea is that you don't spend a lot of time there. You spend a lot of time in your team account. And so if anything, you're just constraining other members of your team, but you should be able to work out those conflicts as a team in your daily stand-up, as opposed to trying to get all of the developers across all the teams coordinated on that staging environment. So staging is just a quick stop. If something's not right, if you have to roll back, then either we're doing compensating commits, or we have ways to revert back an environment to the previous known good state. So you would either commit a fix to get staging healthy again, or revert back. And so this has helped remove that staging environment as a bottleneck for the teams.
So you implemented what a lot of people are talking about, the concept of shipped left, either for security or for QA or for development. Everything is moving closer to the development teams to allow them to move quicker, have less, I would say, dependencies also in software and on other people, and allows them to move a lot faster and allow them to. But you also said the fact of the QA people, which the team was disbanded, but those people they were embedded into these teams themselves, I assume?
Yes.
Which made, firstly, I assume the quality of the QA better in each and every team, and not only one overseeing team to manage the whole thing. And it made them move a lot less faster.
Yeah, a few things happened with that. So first of all, just to be clear, we didn't lose any team members. We actually hired more because we needed to make sure there was enough to go around. But now they weren't context switching. They weren't having to think about all the different applications. One in the morning they're working on this team's app, in the afternoon they're working on another team's app. So now the teams are able to just focus, and you've got test engineers that are specialized and experts at their team's systems. And so then they can go deeper and deeper into the automation and so forth.
So a question which came in from I think it might have been the audience or somebody else over here on the chat was, how does your Git flow look like for promotion between these different environments, from your dev teams to staging account, et cetera, and further on until you get to production in front of your customers?
Yeah, good question. So when developers are working locally, so they're working on they're writing code on their local laptop, and they're deploying to their personal developer account. Git's not involved, right? You're just writing code locally, and I'm doing a CDK deploy. No Git commits necessary, no pipelines. That's just very fast feedback. We wanted to get that as close to the metal as possible. But then with the pipelines, we create a pull request where the QA team can then pull that pull request down and deploy it to their own. The QA team all have their own individual accounts as well, separate from the team account. So QA can deploy that branch to get their own manual testing if they'd like. But at that point, once the pull request is approved, it gets merged to the trunk, which we try to do within 2 to 3 days. Once it's merged to trunk, that's when what you see on the screen starts. Everything on that screen is triggered from a commit to the main branch. And so the promotion between each of those environments is not through pull requests or branches or anything like that. It's not like a GitOps model where we're doing pull requests to get between environments. What happens is it goes to main, and then Code Pipeline has a single pipeline execution that spans all of those environments. And we have manual gates in Code Pipeline where a manual approval needs to happen to go from the integration accounts to the staging account to the production account.
And those capabilities are pretty simple to introduce into Code Pipeline itself, correct?
Yes. Yeah. So a manual approval is a first-class construct in Code Pipeline, and we added those to our opinionated CDK construct. So whenever a developer creates a delivery pipeline, they get that for free. They get those gates added. Now they can go in and turn them off if they'd like. If If they're like, hey, we've got enough automated testing, we want to go straight to staging, they can do that.
And how long does that process actually take from, I would say, from once it gets into main until it goes further all the way up to production until it comes in front of your customers?
So the teams are trying to get to production a couple times a day. So once that changes merge, it might take an hour or two for that change to make it all the way through into production. I mean, it can be as fast as 20, 30 minutes, but it can be as long as, it should be less than a day, but it can be as long as a few hours.
I assume it will depend on the kind of testing you have to validate based on the change and if it's acceptable and can go further down the pipeline. Yeah.
Yep. One of the things the teams have been doing also is they've adopted feature flags with split IO. So they will take changes that they want because they see the value in keeping the pipeline moving and achieving that flow. And so if there's something that's higher risk and they know they're going to have to do a lot of manual testing on it, they'll put it on a feature flag and then just limit it just to internal users and then eventually to beta users to be able to slowly roll things out. But it allows us to decouple the releasing of software from this deployment pipeline. So things can go to production, but they're still turned off in production. And so that's one of the ways the teams found to keep these pipelines moving.
So I'd like to kind of shift to a different focus at the moment because I assume your daily work is not only managing the development of the software, but part of the thing is also managing the cost. And we talked a little bit before about the fact of creating new accounts has no cost allocated to it. Of course, the resources which are in the accounts, which are done. And I assume the more and more accounts you had to find a way to kind of control what was going on. I remember in my days in data centers, we had server sprawl, then we had cluster sprawl on VMware, and then we had clouds. People are talking about everything, resource sprawl, which is coming and growing more and more. You have to find a way to control that. So
yep.
Can you tell me a little bit about how you did this?
Yeah, it's one. I mean, creating new accounts was the easy part, but then managing what the devs were doing in those accounts became a little more challenging. So one of the things we did was we created automation that would provision budgets, AWS budgets, in our master account for every developer account. And so it's just another pipeline that runs, and it queries the organization API to get a list of all accounts, spins through all the accounts, and then applies a default budget to the account. The budget is then wired up to an SNS topic that goes to many different places. It'll email the developer when they're over budget. It'll email the developer's manager when they're over budget. It'll also use AWS Chatbot to drop a note inside of their Slack channel anytime they're over budget. And the whole idea here is we wanted fast feedback again. Yeah, we want to let devs do what so what this is what it looks like to be able to define those budgets. So inside towards the middle, you've got a list of teams. And in this case, the owner for the foo team is Alice, and she's got which channel that team lives in Slack. All of her developers would have notifications roll up to that Slack channel, and then you can do overrides. So maybe Bob is working on some ML project and he needs a larger budget for a period of time. We would just create a pull request against the budget pipeline, which would increase Bob's budget. We use daily budgets, by the way, instead of monthly budgets. Monthly budgets, it might be too late. You might have overspent, and it'd take too long before you get that feedback. So daily budgets. So if you go over on your daily budget, you'll get a notice, and then you can just create a pull request to have your budget increased for different one-off situations.
You said you integrated this with Slack itself?
Yep. So this is what the CDK looks like. So we created CDK that loops through all the accounts and then configures with CDK a chatbot, an AWS chatbot Slack channel configuration. and then hook that up to the SNS topic so that as those budget alerts go out, not only do they go to email, they also go to Slack. I think we have an example of what that budget alert looks like. Yeah, so this is in one of our Slack channels in one of the teams. So you wake up in the morning, you come in the next morning, and you and all your team members already know who went over budget for the previous day. Sometimes they're celebrating with this. It's like, all right, cool. It's good to see that Casey's finally getting into that project, and he spun up all those Kinesis streams, and okay, he's obviously doing something. But then it's a good reminder that, okay, that exceeded what we thought it was going to be. Let's reset the budget value for that. So it's just forcing us to be thinking about cost early on.
And I'm just trying to understand, you said you're using CDK to do this. For those that are not really aware, CDK is the Cloud Development Kit, which allows an infrastructure as code tool to deploy AWS resources. But I see you said in your previous example, you're also doing things to interact with Slack. How does that kind of work?
Yeah. So Slack is, we don't use Slack is a two-way way of doing operations. It's just for notifications. So we use CDK to provision things like the budgets and to configure the integration between the budgets and Slack. And then we're hands off at that point. So we run CDK the one time to configure the budgets and Slack. And then every day, the budgets just continue to look for overages, and alerts go to SNS, which end up in our Slack channels.
And of course, if people on which are viewing the stream at the moment would like to learn more about CDK, you can tune into Adam's session towards the end of the day. You'll be diving very, very deep in how you can use CDK with ECS. So I'm going to stop at that point now and not take away all of his glory for later in the session. So getting alerts is nice. And of course, I gather getting alerts in email is also nice, but now we want even more visibility. So you get your Slack channels, you get paged, et cetera, et cetera. But visibility is nice. You also have to do some kind of thing about saving money, because resources which are running all the time, they accumulate costs. So did you do anything for that in Gaggle?
We did, yeah. So it's one thing to get notified, like you said, but we wanted to make it easy for developers. So we'd ask them, hey, please shut off your ECS services after hours. Well, that's kind of painful, and they'd forget. And so we said, well, let's make it easy. And so we pulled in Cloud Custodian, an open source project created over at Capital One. And so we have a pipeline that continuously applies our Cloud Custodian policies across all of our member accounts. So this is constantly running. And some of the policies we wrote are off hours, on hours policies. So here's an example of the off hours policy on the left. So this runs, and what it's doing is if it's after 6 o'clock Pacific, it goes through and sets the desired state of all the ECS services to 0. And so this goes, a developer may have been working on an ECS service. They had 2 or 3 tasks running. This just goes through and pins them all to 0. So it shuts down all ECS services that are running in a developer's accounts. And then the policy on the right says 8 o'clock Pacific, we go ahead and revert the desired count back to whatever it was when we shut it off. So developer leaves, they don't need to think about it. All the ECS services scale in to 0, and then they come back the next morning and things have already scaled out for them. They have the ability to fine tune these. They can put custom tags on their ECS service to have it be exempt from this policy, or if they want different windows. Not everybody's in the Pacific time zone, so they may want different windows on when their downtimes are. But so this makes it very easy for developers to not have to think about and remember to scale in or scale out their services. It just happens for them. Nights and weekends, now we're no longer paying to run these development applications. And
I assume it saves a decent amount of money for your AWS account, for your bill.
Absolutely, yeah. All of our accounts, right? This is running on all our non-production accounts.
You mentioned before in the beginning of the session the fact of you're using kind of shared clusters, CPU focused tasks, memory focused tasks. For me, that sounds that it's kind of difficult to understand if it's a shared resource, and specifically from your perspective of managing cost per budget, per team, per application. How do you differentiate between different applications which are using a shared resource?
Yeah, this was a tough challenge for us. We'd have these clusters, and 3 or 4 teams might be sharing the cluster, and all of a sudden, cluster usage goes up, and we're trying to figure out why is this cluster so expensive? Where did the charges go? So we created a tool called ECS Chargeback. We open sourced it as well, and so ECS Chargeback, the way that it works, see on the picture, it's just a Lambda function. The Lambda function is running every 5 minutes, and it's doing a few things. It's using the AWS SDK to query a list of clusters, and for each of those clusters, the services, and then grab the task definitions associated with each service. So it's pulling in all kinds of data, because what it needs to know how much memory and CPU is being reserved. Right? When you create a service, that service has a task definition. The task definition says, I need 4 gigs of memory and 1 vCPU. All of that's explicitly listed out in your task definition. So now we know, okay, this service is going to be reserving this much CPU and memory. We also query CloudWatch to grab what's the service actually using. That's great that it's reserving 1 vCPU, but maybe it's only using 10% of its CPU. So we grab the actual utilization and the reservation. So now we have both of those bits of information. Grab the cost from the AWS Cost Explorer SDK to get what we're actually paying per cluster. So we can go back and look for the instances in the cluster. Here's what our spot price. This is what we're paying for those spot instances in the last 24 hours. We look at the specs for each EC2 instance, also from the SDK, how much vCPU and memory is per each instance type. And then we cache all that data because a lot of that stuff never changes, right? Our billing is good for 24-hour period. EC2 instance definitions much longer. We cache out in S3. And so then we can take all that data and then create new custom metrics that we push back to Datadog. Those custom metrics are things like what percentage of the cluster cost can be allocated per service. So if a service has so many tasks running and those tasks take so much memory and CPU, we can then infer what percentage of the actual spend can be attributed to that service. And so we get this nice dashboard in Datadog, which shows us cluster cost versus cluster waste. Cluster waste is this other number that's very helpful. It tells us what's the difference between what we're reserving and what we're actually utilizing. If we're reserving 4 gigs of memory and only using 2, you're paying for 4 gigs because ECS is going to commit that memory to that task. And so this allows us to quickly zoom in and say, okay, in this case, we saw a lot of waste in the CPU cluster. And so we're able to then drill into that and say which ECS services have the most utilization and reservation in that cluster, and then go to those teams and say, okay, your service has a very high amount of waste. Why don't you update your task definition and bring down the amount of memory or CPU that you're reserving for that service? It's unnecessary. It's waste. And so we're able to really tighten up the costs and know where to dig with this tool.
So I see, of course, you're not only using native AWS tools here. Of course, there's reasons for using third-party tools, which are partners of ours, which interface very, very well with our APIs and makes it very simple for you in order to collect this information, analyze the information, and create actions or things that you need to do in order to understand or optimize your infrastructure.
Yep. Yeah. Datadog was the right tool for this. Because we also collect stuff outside of AWS, and Datadog provides a single place for us to collect all these metrics and visualize this.
Okay. So logs. I know that developers, or everybody actually, people which also operate the systems in the end, love logs. So what are you doing with the logs? I mean, of course, these logs have to be emitted from each of the containers and the applications. But how do you handle your logs, and more importantly, I would think metrics at Gaggle based on your applications?
Sure. So for our ECS services and our Lambda functions for that, all of our logs are collected and sent up to a OpenSearch cluster. So we use
AWS OpenSearch?
Yes. So we use AWS OpenSearch to aggregate all of our logs. We were previously running our own Elasticsearch on EC2, but late last year we moved away from that and went all in with OpenSearch. It just provided we wanted to get out of the business of managing the Elasticsearch cluster ourselves, and the cost well outweighed the benefits of not having to manage that anymore. So we stood up an OpenSearch cluster. We're able to then use inside of OpenSearch. You've got index lifecycle rules, so we could automatically move logs into to ultra-warm, where you're paying less for that read-only data, and then ultimately purge those logs all through index lifecycle rules. We use the managed Kibana that is available with OpenSearch, and then we get all of our logs into OpenSearch with FluentD. We run that as an agent on the ECS container instances to collect the logs from all the containers and ship them up to OpenSearch for us.
Did you need to do anything specifically in the ECS task? Did we change the way you wrote your code, or is that a simple configuration based on?
Yeah, it depends. Teams are doing a couple different things. Some teams use Log4j, and then they use a Log4j appender that uses FluentD to send off to OpenSearch. Other teams are writing to the console, and then that console will either configure in the task definition to use the appropriate driver to send those logs off to OpenSearch for us. Or in some cases, some teams are using CloudWatch, which we then aggregate through a Kinesis Firehose and then send that to OpenSearch as well. But all paths lead to one OpenSearch cluster. So it doesn't matter how you get it there. You got to get your logs in OpenSearch.
Awesome. Do your teams operate in a model of like you build it, you own it? Or do you have an operations team or a DevOps team? It depends on how people like to call them, which manage the production applications. And the reason I'm getting into this kind of question is because usually people get paged at the wrong times of the day, in the middle of the night, weekends, whatever else it is with problems. And the first thing I want to do is try and understand what's happening in the system. So for that, you have a way of tracing application calls, flows. What do you use for those kind of things at Gaggle?
So to answer your first question, yeah, we prescribe to you build it, you run it teams. So the teams that are writing the code and running their pipelines, they're responsible for their application running in production as well. So they set up their own alerts in Datadog that notify the appropriate people, and they're responsible for keeping their applications healthy in production. So for the alerting, yeah, that's going through Datadog. We've played a little bit with tracing. We looked at Amazon X-Ray for that, but it's pretty expensive, and it was tricky for us to get that right. The cost of the service versus getting valuable data out of it. So we tend to only use tracing when we absolutely need it. Okay, we've got something that's misbehaving and we're not able to diagnose through logs or through metrics what's going on. Let's go ahead and turn on tracing for a subset of transactions for a brief period of time, see if we can collect the data to answer the question. There is an infrastructure engineering team. You can call it a DevOps team, but they don't own these applications in production. They're building constructs in CDK, and then they what they own. They own a shared Python module that contains the reusable CDK constructs, the opinions on what does an ECS cluster look like, what does an ECS service look like, what does a Lambda function behind an SQS queue look like, and those higher level constructs are then made available to the dev teams, and then the dev teams consume them, use them, and run them. So developers can make pull requests on those. Developers can, and the infrastructure engineering team may embed with those teams to help them get up to speed with how to do pipelines and how to use OpenSearch or so forth. But the dev teams ultimately own it, not the infrastructure team. They don't own these applications in production.
Is there any kind of, I would say, wisdom or things which you've learned either by being burnt or things that you learned along the way that you would like to share with the rest of the people watching today, of kind of patterns that you understand which might be used or useful for other people to look at?
Sure. Let's see. Use CDK. CDK has been a wonderful investment.
CDK is awesome.
Yeah. Don't. I'm stealing your ClickOps term, Mesh. Don't prescribe to ClickOps. Don't click the blue button in the console. Write it as code. Store it in the repos. Go all in on pipelines. Things like our budget. Our budgets. We created a pipeline for that, and it makes it very nice to set it and forget it, and then people can self-service create their own pull request when they need changes. So everything, not just your applications, but all of your interactions between teams work best in a self-service way where there's some sort of a pipeline and a pull request between teams. That's been great. Creating that third-party module with this reusable CDK constructs has been really cool because it's just code. It's people are used to writing classes and libraries, and so it's a concept that is very common to both the infrastructure engineers and the app developers. So invest in creating that place where you can build your own CDK constructs. What else? Control Tower has been great. We use AWS SSO to help with getting across accounts. Developer accounts has been a huge lifesaver in driving that lead time down. And just watch the costs because developers will use it. I mean, that's the goal, right? You're giving them these accounts so they can innovate, but you got to make sure they have visibility. Don't centralize that stuff. Push it back to the team. The team will self-manage. When we made it visible to the team who was spending what, they took care of it themselves. You don't need a central team to manage the cost. Just make it visible. Likewise with the ECS services. Once we made it visible for teams to know what they were spending, right? When it was all a shared cluster, you could kind of fly under the radar and you're like, no one's going to know that it's my service that's wasting things. But once you shine a light on it, people are like, okay, cool. Yeah, we can take it from here. And so making things visible is critical to sharing the load on these things.
How did this transformation work out for Gaggle? And of course, I'm doing this for a reason. You shared a slide before with me about how this, we were talking about the fact of your lead time of deploying. We can see the change here of the fact of how much lead time it does per developer. Besides the fact of the graph, what did it change for the developers themselves? Did it have any impact on them?
Yeah, so the developers feel a sense of productivity, right? No developer likes writing code and then waiting 3 days and then hearing about problems, right? When I'm done with something, I don't want to hear about it again. And so pushing it up to a branch and then crossing your fingers and thinking is no news, good news, it's miserable. And so developers have really loved this process. What was cool was we started with one team, and the one team went all in with these new tools and techniques, and you could hear their energy and enthusiasm about it. And other teams got jealous, and they're like, well, we want to do that too. And so the teams have really embraced this model. And as you can see, the numbers here, so the red is lead time. How long did it take for changes? We're seeing 47 days. That's now actually around 10 is where we're running for lead time for new changes. And deploy frequency is up over 6, how many production releases we do per day. And so many people were critical in this. Got to shout out to people like Tamir and Jim and Keith and Jerry and Jeff that helped build all of these systems for us and work with all the teams to make this all happen and make a better place for the devs to get stuff done.
Awesome. Looks like an amazing journey. Before we close out, I want to ask you one last question, which I was going to ask before, was the fact, what is next for Gaggle in the container world and ECS? Where are you looking to next? What do you want to do?
Team's doing a bunch of work right now on looking at using Graviton instances. We want to take advantage of that price performance optimization that you can get by running Graviton for our ECS container instances. But this was also forced on us because we started buying new laptops for new devs, and they were getting the new
M1s?
ARM. Yeah, the new ARM, and they're like, hey, I can't run these images locally. So we quickly had to solve how to build pipelines that would create both ARM-based and Intel-based images. Shout out to Mike and Jared for making that happen. And so now we're able to, in our pipelines, create both images. And so we're starting to look at, okay, that's great for local dev. Why don't we start doing this in production as well? So adding Graviton-based instances to ECS clusters and then running those platformed images on there is something we're looking at. And then we'd like to be using capacity providers rather than spot fleet requests and step scaling like we're doing now. Capacity providers provides a much nicer way to manage the scale out and scale in of EC2 instances in your cluster based on load. So those are the two things on the team's radar right now.
Awesome. I want to thank you for your time today. If anybody would like to contact you, reach out to you, speak to you more, dive into your story, or maybe just to chat, how can anybody find you or reach out?
Best way is on Twitter there at Nectos. And also you can find more about Gaggle at gaggle.net. We're always hiring, so take a look at some of the openings that are available there.
Casey, thank you very, very much for your time today. It was awesome hearing your story. We're going to close the session now and move on throughout the rest of the schedule. Thank you very much for your time.
Thanks, Mesh.
I really like to start my morning going outside on the patio. The morning standard meetings very important for me because I can know what the team is doing. I think my job is mainly creating an effective team to deliver the most value to customers. I really like when I see my reports growing on their career and also when people are excited about the work that they deliver. We have sister teams also in Cupertino, Seattle, and San Francisco. AWS managed to get everybody on the same page, regardless of which team you are. End of day, learning how to play the guitar. That's one of the biggest challenges outside of my work. I'm Helbert Maisch, a software development manager at AWS in Vancouver, British Columbia.
Today, more and more people are running their workloads in containers for better resource efficiency, workload portability, and flexibility. That's why AWS created BottleRocket, a Linux-based operating system that is purpose-built to run containers. BottleRocket updates in a single step, and updates can be rolled back if necessary, giving you fewer error rates for OS updates and increased uptime for containerized applications compared to general-purpose operating systems, which update package by package. You can easily automate updates to your operating system by using container orchestration services such as Amazon EKS, helping to reduce your management overhead and ultimately cutting down on your operation costs. And because BottleRocket includes only the essential components needed to run containers, it effectively boosts resource utilization and lowers security risks. By leveraging BottleRocket's open source development model, you can make your own code changes and produce custom builds that support your preferred orchestrators and build tools. You can also submit your changes for inclusion to the AWS BottleRocket builds. AWS provided builds come with 3 years of support, giving you a single point of contact for all your infrastructure support needs, including operating system support. Build with confidence and optimize your container infrastructure today using BottleRocket.
It was awesome. Great job, Maish. Great job, Casey. This is the part where if we were all together in a conference room, everybody would applaud. So feel free, go ahead and do that in front of your screen. We're all about the full event experience here. Seriously though, getting to see an example of how a customer is using the platform, at least for me, is always a great way to get to know that platform better. It makes it even cooler when it's a customer like Casey and Gaggle. As the parent of a daughter in middle school and a son who's in his first year of high school here in the United States, I'm a huge fan of the work that Gaggle does. We've got an extra minute here, so I want to tell a story about my two kids who are in their last week or so of school here, and so I'm sure may even actually be watching this, as weird as that sounds. In the United States, every high school is essentially captured by an application ecosystem. It's Google, or it's Microsoft, or it's Canvas, or it's a combination of them. In these last weeks of school, when things are slow, my daughter has taken to writing Civil War era letters to her brother using the Google mail system that they have in common, since they're both in the same school system. They are incredibly funny and hilarious, and I can't imagine what a system like Gaggle does when they start seeing some of the content that she's sending in there, not because the content is appropriate, but just because it's very out of place in an educational email system. Great work to Gaggle. You know, Casey's a great example of the kind of people and the technologists that we have as part of the AWS Heroes program. If you're interested in learning more, it's Gaggle, GAGGLE.net. And check out what they're doing and some of the impact that they're having on the lives of students. One of the things that I took away from that presentation was that deploying production apps isn't a one-time event. It's something that happens multiple times, but also evolves over time, both with the application as it changes, as well as the company itself that is doing the deployment, and even the teams and individual developers who are writing the code. Understanding not just where you are today and the challenges that you have to solve, but knowing that the AWS ecosystem is prepared to help you solve whatever the next business challenge is that you run into, is to me a huge part of the value proposition of the ecosystem. The amount of magic that Casey and the team have built into using multiple AWS and third-party tools specifically to manage cost was, to me, really cool. Repo-driven daily developer budgets that can be managed with a PR is something I haven't seen before, and it sounds like a really cool demo waiting to be made. So we'll definitely talk about that with the team and see what we can find out. Speaking of AWS Heroes and business value, that's actually a really good segue into our next presentation. If we can, let's pop up the agenda that Inbal shared earlier, because there's a quick change that I want to make here. You know, good coding practices say that we're supposed to go back and remove code that's no longer in use. And for this next session, Luke doesn't need any help from me whatsoever. So let's go ahead and edit that real quick and make sure that both the spotlight and all of the shine that we can put on this session is directly on Luke. He doesn't need me, and I am more than happy to trim the dead weight that's out of there. So without any further ado, Let's kick this over to Luke and talk about a topic that couldn't possibly be more relevant to companies who are doing work in the cloud and to developers who are building on top of containers. So, Luke, take it away.
Hello, everyone. Welcome to Container Security and AWS Container Services. I'm super excited to be covering this session. I think you'll find a lot of golden nuggets. I'm going to be sharing my AWS hero story. And in addition to that, I'll share a couple of important principles around container and Kubernetes security in the AWS context. Some of it will be more on the agnostic side because containers and Kubernetes obviously are infrastructure agnostic. And so I hope you'll be excited for this ride. And let's go ahead and actually just jump in. So for starters, my name is Lukonde Mwila, or you can call me Luke, and I'm a principal technical evangelist at SUSE. That is always such a mouthful, like my mouth gets tired whenever I put that out. I'm also an AWS hero and a HashiCorp ambassador. And just for a little bit of background on my career, I started off in application development with a focus on web and mobile app development. And then I transitioned into a more DevOps role. And in that role, I also focused a lot on solution architecture and cloud engineering, doing a lot of automation engineering with tools like Terraform. And after that, I ended up where I am now, which is in more of a developer advocacy or technical evangelism role at SUSE with a huge focus on the cloud native space. So just to start off with, I want to talk to you about becoming an AWS hero. And so this is my personal story and my perspective. And I'm glad I get the opportunity to share it because I have had a couple of people reach out to me online and ask me how it actually happened. So this may not be exactly the same as other heroes, but perhaps there'll be some principles in this that could potentially inspire you or help you on your particular journey if it's something that you're pursuing. So for starters, I like to believe that I took a reactive and a proactive approach to what I call AWS Community Care. That sounds like some kind of a program, AWS Community Care. But really all I'm talking about is the technical community, and that will consist of developers, DevOps engineers, SRE, solution architects, anyone that's involved in the AWS community space. And so I'm sure you'd agree with me that there is a ton of stuff out there when it comes to the AWS landscape. So many different services, so many different components, and a lot of people are trying to figure out and piece these things together. And so what I did was essentially I started taking a look at what people were struggling with, what challenges they had, and I would strive to build content that would help other people on those particular issues. So that would be what I call the reactive approach. The proactive approach was I'm an AWS fan, so there's a lot of cool services that I would love to try out and integrating with different things. And so what I would do is actually try and think of different use cases or scenarios that would be helpful, whether it's in a business context or for a small startup project or just a side project, and essentially build content out of that, primarily whether it was technical articles or meetup talks. But the goal was to create use case content that I thought would be helpful to other people. A huge inspiration behind this was essentially just trying to overcome some of the help other people overcome some of the challenges that I faced when I was doing research, looking for resources that would help me at my job when I'd be working with AWS tooling. And so I was essentially trying to help the next person to make sure that they don't have to deal with the things that I faced. And I think another thing that's really important in this space is building trust. And some of you might be thinking, well, how do you build trust with people you've never connected with? And it's essentially just the content that you put out, whether it is a meetup or a video or a technical article. I think just making sure that the stuff you put out actually works. That's what people are looking for. A lot of developers are searching for solutions online and they'll Google for stuff. And so when they land or come across your particular material, what's the experience? Can they follow everything right through to the end and see that, hey, that actually worked? And it's so refreshing, and it's great when you get to meet different people online and they reach out to you and say, hey, this particular article really helped me, or this video was great. I think to this date, there's one particular message I got from I think he's a tech lead at one of the banks here in South Africa, and he shared with me, he said, like, we've actually been working with this complex solution that involves ECS, and your article has helped us in a great way. And so that is essentially, that was the goal, you know. So there really, I really wasn't actually at a point where I was striving and saying, I got to be a hero. I got to be a hero. You know, I thought it was awesome, but I was really actually just focused on helping other people in the dev community, and becoming a hero was a side effect and of that. And I saw someone else, I think, shared a post similar to that. And so that should actually be the driving point. And I hope that that can be helpful for other people who are aspiring towards becoming an AWS hero. It's basically keeping the developer community and the people involved in the AWS space at heart, and wanting to assist them or guide them on the enablement journey as well. All right, so I'm going to segue now more into the particular topic at hand. And I've got some cool stuff lined up for you. I will be talking a little bit about ECS, and I will also then venture into EKS. And a lot of the things that I'll be discussing are actually born out of a particular project that I was involved in. I want to share some of the security principles that we learned along the way, some of the things we applied, and some of the things I only learned afterwards. So I hope that particular journey will be helpful for you. But I have to start off by saying that it is such an exciting thing that containers and Kubernetes have gone mainstream. This is a really exciting thing, and the CNCF shared this in their most recent survey. And so what this means is a number of organizations around the world are adopting containers and Kubernetes at a large rate, or a fast rate rather. However, the downside to this, and I think this is a norm in our industry, or in the tech space rather, adoption of a cool tech or a popular tech usually goes far ahead of adoption of best practices. And that's a problem, because a number of companies or organizations will be adopting this technology, but if you're not implementing the best practices, there are usually other ramifications that come along the way, or down the line, and that actually in turn ends up, you know, adding a bad reputation to the particular technology, when it's not the technology that has an issue. It was the fact that best practices got left far behind and people were too excited about adoption. So this is not in any way a slight against, you know, containers and K8s going mainstream. That's exciting, but I'm very passionate about trying to help with best practices, catching up to that, and especially security best practices. And so that's what's going to be the focus today. And so, as I mentioned, I'm going to be sharing what I'm calling a container orchestration story, because ECS is also a container orchestration tool. The project that I was on was essentially a financial solution that consisted of multiple microservices. And so, for starters, we worked with ECS. And the main reason for actually going with ECS was because a number of people in the team were fairly competent with working with AWS. And we thought that ECS was going to be particularly helpful for us because it did the job of orchestrating our containers, but also it does a really good job of abstracting away a lot of the components that deal with the complexities of container orchestration. So to date, I still advocate for it a lot because I think it's an excellent tool, especially for people who aren't necessarily inclined to the operator side of things, and they're looking at, they really are just focused on, hey, look, I need my containers to be orchestrated, and I don't have too much time to get involved in all the nitty-gritties of orchestration. You know, so I think ECS is great for that. And this might be a bit of a shameless plug, but it's one of the reasons I love Copilot, because Copilot, you know, goes a step further with that. So anyway, to get started, this project was one in which, as I mentioned, started off with ECS before we eventually transitioned to EKS. And so what you're looking at over here is a technical architecture diagram that kind of shows the landscape of the solution. Not exactly what it was like, but very similar, kind of downsized it a little bit over here. And some of you might be thinking, okay, I don't see containers, all right? How exactly does this fit in? Why am I looking at all these different components, from an API gateway, a VPC link, S3, etc.? Well, the reason is, this actually is one of the reasons that Kubernetes and container security need to become a lot more popular, because the landscape of container security is very vast. And there's so many different components that you need to consider. It's not just your containers. That's sort of looking at it from a micro level. And so from a macro level, security actually will start with the infrastructure around it. And so I thought it would be useful to actually cover this, to just show an example of a solution where we were trying to make sure we had container workloads running privately in the AWS network. And by, in a private sense, I essentially am speaking about the fact that we wanted to make sure that all of the networking, the network traffic rather, was enclosed to the AWS cloud environment. So I'm simply going to walk through this just so you have a better understanding of exactly what's going on with the different components. I like to call this my omelet. So I did create a technical article about this, and I have a picture in that article of an omelet. And I say there are lots of good stuff that goes into the omelet, but you need to know why the different pieces or components are in there. So for starters, at the heart of this, you'll see there's ECS Fargate. And so we were looking for a solution for container orchestration. But in addition to that, we didn't want the additional layer of managing our nodes. So that's why we went with the serverless engine of Fargate. And so we opted for that instead. And then you'll see over there that we've got our services and we've got our tasks. And I usually like to draw parallels between ECS and Kubernetes, because sometimes they're, people are trying to figure out, well, what is that? So a task would essentially be the equivalent of what a pod would be in Kubernetes, and a service would be the equivalent of a deployment, which is essentially managing them to make sure you have certain workloads running at all times. So your tasks would be what would be ephemeral in this case for your particular containers. And so you'll notice that there are no public subnets at all. So this is closed up. And so we've got our we've got ECS Fargate, and we've got our service running our tasks in private subnets. And then to proxy traffic to those particular tasks, we had a network load balancer that was associated with those private subnets. Now, as you'd imagine, the next question is basically, oh, okay, well, how are we going to access our application if the network load balancer is associated with, the private subnets? Why not put that in the public subnet? So instead, what we did was we opted to have an API gateway so that we could add additional rules and throttling of traffic on that particular front. And then that would be our single point of entry for our workloads. And then any traffic coming through there would essentially be proxied through a VPC link, which would integrate with our VPC service endpoint. And that would be connecting to our network load balancer to handle all of the traffic there. So we still keep a closed network environment. And then right at the front, our single point of entry would be our API gateway. Now, when it comes to working with ECS, there's still other components. So in our situation, we weren't using Docker Hub. We were using ECR to store our container images. And so you'll notice that there are VPC endpoints over there, or VPC private links, as the diagram shows. And this essentially gave us that private network integration to specific AWS services. The alternative would obviously be to have a public subnet. And in that public subnet, you can have your NAT gateway and then also have an internet gateway attached to your virtual private cloud, and essentially have a way of routing traffic through to the internet to connect to the different AWS services. But in this approach, having the VPC endpoints allowed us to keep things private to integrate with specific services. And so that's why ECR is over there. All of our container images were stored in ECR. And if you're wondering what the connection with S3 is, the container image layers for ECR are actually stored in S3. That was something that was really interesting to find out. And so that was why that particular connection was there as well. And so I hope that this is one of the things that can just sort of broaden your mind when you're thinking about securing your containerized workloads or your container orchestration platform, to understand that there's so many other pieces around that you have to be considering. And this is obviously it's use case specific. It was our scenario. It was one of the requirements we had, that we needed to keep a very private network. And so you might have something different, but the important thing is to understand that you need to consider the different security pieces around your workloads as well. And in this case, it would be, what does that look like from a VPC perspective? What does that look like if you're going to be having public network traffic to connect it to the internet, for example? Or are you going to follow an approach like this where you connect to different AWS services in a very private way? So this is to sort of like have you thinking from a broader perspective around your container workloads and thinking around the infrastructure side of things and the different pieces over there as well. And so I certainly hope that this is something that will assist you in that particular regard. All right, so just in case you're interested in actually delving deeper into that, I did mention I have a technical article that deals with that particular topic, but also I have all of that infrastructure built out in Terraform. So that's, Terraform is an infrastructure as a code tool, so you can use that to provision all of that infrastructure. And so this slide over here is just in the case that you wanted to visit my GitHub repository. It's one of the repos on the landing page. It's AWS API Gateway VPC ECS Fargate. If you wanted to provision that and actually play around with it. So it's cool that a number of people have actually been able to test this out and use it. And you'll see the open source license over there. So feel free to contribute to it or use it however you see fit. All right, so as I mentioned earlier, in that particular project, we initially started off with ECS, but then as we progressed through the particular project, we eventually transitioned to actually using Kubernetes, and so specifically using Amazon EKS. And that was certainly a big jump, because ECS and Kubernetes are different. You might have heard me mention earlier on that one of the things I really love about ECS is the fact that as much as there are a lot of components that are taking care of the container orchestration and managing all of that complexity, it gets abstracted away from you, and you don't have to interact with it from a configuration perspective as much as you have to on the Kubernetes side of things. But nonetheless, we ended up working with Kubernetes. And if that is your particular situation, I thought this would also be really helpful to start off with looking at the landscape of your Kubernetes cluster and what it looks like to secure that. And something that I love to say that a friend of mine has shared with me is if you were going to secure anything, like even outside of the context of containers, just in life, if you were securing some kind of building, there are usually two things that will inform that particular process. The first thing will be what exactly are you what valuable thing are you trying to keep safe? The value of that particular item is what is going to inform the measures you put in place. But in addition to that, understanding the vulnerabilities as well are what will inform your decision making. So whether you're going to have high walls, whether you're going to have security presence in terms of guards or dogs, etc., all of that is based on particularly these two items. And so this diagram over here depicts a Kubernetes cluster, specifically the blue block over there. And what we have are two gray blocks, and the block on the left is representing both the control plane and the data plane. And on the right-hand side, we have the worker plane. And so, as I mentioned, the Kubernetes security plane is very vast. And I think it's very important to start off with understanding what the potential attack vectors actually are. And so I'm going to take a bottom-up approach, starting from the lowest level, which would be your infrastructure layer, so to say. Understanding your hosts as well could potentially be attacked. So you need to recognize the fact that Kubernetes has a lot of networking that takes place within it. That's one of the main things about Kubernetes. And a lot of that gets abstracted away, which is great because it's complex stuff. However, there are specific ports that need to be open on your underlying nodes in order for traffic to work, in order for the Kubernetes cluster to work the way that it should. However, you need to be aware of what ports need to be open in order for you to not expose the wrong ports, because all of that could increase the chances of a potential attack. So that's one side of understanding your infrastructure there with the hosts. But in addition to that, you also want to be able to secure the operating systems on your hosts. Some of you might have heard something that's very popular amongst container, the principles when it comes to container security is to not have your containers running as a root user, because you don't want the operating system to be taken advantage of, or because of potential attacks from a malicious software, or someone that might gain access through that particular means. And so other things that you could do with securing your host could be making use of tools like Secomp or SE Linux or AppArmor. And these tools essentially allow you to be able to secure different the hosts by applying different profiles to narrow down what containers are actually allowed to do, programs and processes on their hosts. And the cool thing is you can actually carry this out using Kubernetes. For example, and I recently put out a video on the Rancher Labs channel explaining this using the example of using AppArmor with your K3s hosts. And you could essentially store your configurations for the AppArmor profiles in a config map, which is a Kubernetes resource. And then to make sure that those profiles are actually loaded correctly with the relevant rules on what can be done and what shouldn't be done on the different nodes by making use of daemon sets. And daemon sets are essentially pods that are going to run on every one of the nodes. And so that's a really cool approach. And you can apply some cool principles or models like GitOps, because if you have your config map with the AppArmor profiles, for example, stored in there, as well as the daemon sets in your Git repository, which is essentially your single source of truth for GitOps, then that can essentially be deployed to all of the different hosts. Now, taking it a step up, getting to the actual Kubernetes layer, you have your control plane, for example. And Kubernetes is an API-centric platform. So everything goes through the API server. And so what you need to make sure of is to ensure that you're securing your API server as well, because all the CRUD-based operations, whether they originate in the cluster or from outside of the cluster, they're all going to go through the API server. In addition to that, there's a lot of traffic between the API server, the scheduler, the controller manager. And of course, all of your cluster configuration is stored inside of the data plane, whether the implementation is going to be etcd, or if you're using a lighter solution like K3s, then you might be using something like SQLite, or you might go with a MySQL database. Whatever the case may be, there's a lot of network traffic taking place. And so you can put certain measures in place to secure all of that network traffic. So if we look over to the right-hand side now, on the worker plane side of things, we've got our kubelet agent, which is the node agent, which essentially communicates with the control plane. And in addition to that, it's going to be communicating with your registry. So in our case, we did have some container images stored in ECR, as well as we were also making use of some images from Docker Hub. So this is the kubelet agent essentially is going to be communicating with different registries, and it exposes an API. So also making sure that you secure that or lock that down. And just lastly, on this particular aspect would of course be your workload. So the actual containers and the pods. And I find that this is usually the most popular area that a lot of teams or people will gravitate towards when it comes to securing their Kubernetes or containers in terms of their particular security strategy. They'll focus on image scanning, which is important, but it's not the only thing to do. And I'll be touching on that a little bit later. But I hope that sort of gives you a good understanding of the big picture. It's really important to understand what are the weaknesses or the vulnerabilities that you need to be considering. And so keeping that in mind, that should then inform the different solutions or measures or steps that you take to secure it. And so this diagram is one that I like to use to show the different dimensions that you would essentially be taking to secure your Kubernetes cluster for the hosts, the cluster components, the authentication and authorization, and the workloads. And this will obviously look a little bit different in the context of Amazon EKS because your control plane is managed, and thankfully you've got a team of experts who are essentially taking care of making sure that it's highly available, the security posture is actually good, and all of the different configurations as it pertains to that. So that's a huge help. But you still have the responsibility of taking care of other things. So in our case, we were making use of managed nodes. We had come from a Fargate solution with ECS, but when we adopted EKS, we were making use of managed nodes. So that is where making use of things like AppArmor or SE Linux would be especially helpful when you're securing your hosts and having different measures in place for your operating systems to manage security there, where your container workloads are going to be running. So in addition to that, an important sphere would obviously be making sure you're making use of certificates, and you're also applying TLS essentially, because you want to have authentication and secure data in transit across the board, because as you probably picked this up as I was talking about it, there's a lot of network traffic taking place within the control plane itself. the control plane and the data plane, and of course, also with the worker plane. So a big win over here is to make sure that you're making use of certificates to secure your data in transit. That way, also the different pieces that are communicating will be able to identify the source of traffic as well. And then, of course, there is authentication and authorization. Authentication is a big one in the context of Kubernetes. Kubernetes doesn't have a mechanism at this point in time of actually keeping track of different identities. So it relies on you essentially doing that outside of the system and then essentially mapping that to the context of Kubernetes, but making sure you have a solution in place over there, and there are different methods that you can make use of for authentication. Then authorization, of course, again, a very popular one here is role-based access control, but there are different methods that you can make use of. There's also attribute-based access control, which is less static compared to RBAC. It's a lot more dynamic if you want to work with specific attributes. There's also a webhook authorizer if you want Kubernetes to essentially query an external REST API in order for it to check the access control for particular users, as an example. But this is also something you can do for your workloads, making sure you're not making use of the default service account for your pods, and making sure they're attached to a specific service account that is also attached to a specific role or a cluster role. And then just lastly, from a container workloads side of things, would be making use of things like pod security policies. I know they're being deprecated, but certain measures like that can definitely be helpful, obviously provided that you're using the right version of Kubernetes. And then there's also policy enforcement, which I'll elaborate on a little bit later, and network security policies, which essentially allow you to be able to control the ingress and egress traffic for the different workloads that you deploy to your Kubernetes cluster. So I know it's a lot, but I think it's highly valuable to be able to actually understand these different things because, like I mentioned earlier on, it's one thing to get excited about Kubernetes and containers and to run ahead with adoption, but you certainly don't want to end up in a situation where you run far ahead and left the best practices behind. So I hope this will help inform that. Cool. So another important concept or paradigm, and we were also making use of this to some degree, is the model of shifting security left. And this is a very important principle, and it's increasing in popularity, which is great. And there are different ways of carrying this out. The first one that I'm going to touch on is image scanning and policy enforcement. And as I mentioned, image scanning is probably the most popular when it comes to people securing their containerized workloads. Whenever I do have conversations with some people and just asking them the different strategies they have in place, it's usually, well, I'm scanning my images, so I think I'm doing pretty good. But there's a lot more. But let's go through the different ones. So as I mentioned over there, executing container image scanning in the CI pipeline stage. So the whole point of shifting security left is to essentially, move, try and catch things early. That's the basic idea of it. A friend of mine likes to use a certain example of, you don't want to have your alarm for right at the stage where you have your jewelry box. So the question that you ask after that is, well, how did they make it all the way into your yard and into the house and into your bedroom, and you only have an alarm when at the stage that they actually get to the jewelry box? And so what you're basically trying to do is to catch things much earlier than that, before they even get to your yard. And so the software supply chain is basically an opportunity for you to make use of that. And so with container image scanning, and there are a lot of good tools out there, a really good comprehensive one is NuVector, and it is recently became open source, was recently acquired by SUSE, but I'd encourage you to check that out. Obviously, other good ones out there as well would be Aqua's Trivi and Sneak as well. And scanning is a really important step, and like I mentioned, it's the most popular one, but it's it's just one way of doing things. And I do want to mention, one of the pitfalls with scanning is, remember, it's kind of like a snapshot in history. So you might run container image scanning in your pipeline at the CI stage, and maybe it does meet the relevant requirements at that particular point in time, but that's based on certain certain updates to the CVE database. And so that is actually continuously going through specific changes. And so you don't want to simply rely on that. So once your image, let's say, meets a certain criteria and now has been pushed to ECR, for example, you also want to be continuously scanning that with based on the updates with the CVE database. And that's also something that NuVector allows you to do. You can essentially connect it to your ECR registry and have the continuous scanning taking place over there for the different ECR repositories based on the database changes, and you can run those scans regularly. ECR also allows you to carry out those scans, but the point is, don't rely strictly on the CI pipeline because that's a snapshot in history. And when it comes to your images finally being stored in a specific repository, continue to do the scanning over there based on CVE database updates. In addition to that, I mentioned policy enforcement in your pipelines. And so what I'm speaking about over here is essentially there are different best practices when it comes to your Kubernetes resources and your containers as well. So I mentioned one earlier, such as running container as root. So you can make use of different tools to essentially prevent such things from happening before they even end up in your Kubernetes cluster. And so whether you're using Kyverno or Datree, you can define your policies ahead of time and essentially run the relevant policy checks even at the pipeline stage as well. And that would be a great opportunity for you to essentially run your checks. And I think this works particularly well with GitOps. I'm a big fan of GitOps, and it's a model or a paradigm that's growing in popularity because a lot of people do love the fact that now you can have your infrastructure as code stored in your repository, and that acts as the single source of truth for your Kubernetes cluster. That essentially becomes the desired state for your cluster that a GitOps operator like Rancher Fleet or Argo CD or Flux will essentially be watching in order for it to reconcile and make sure your cluster's live state or current state matches the desired state. So when you're making use, however, there's still a pitfall over there in that if you don't have the relevant measures in place, whatever is stored in your repository is what's going to get deployed to the cluster. So what you want to make sure is the resources stored in the repo are, meet a certain security criteria. And so a way of doing that is essentially to make use of policy enforcement during your CI pipeline stage. And I have a couple of examples of this in some videos that I've published using both Argo CD and Rancher Fleet. And essentially, after you've built your container image, done the relevant security checks and stored it in a repository, what you can then do is you've got a specific image tag at this point for the version of your application. And what you'll proceed to do is then update whether it's raw manifest files or Helm charts are customized with the new version tag. And at that point, that particular set of resources can essentially be tested with your policy checks to make sure that it meets certain criteria, like maybe always have 3 replicas running of your pods defined in the deployment, not making use of the default service account, not running a root user for your containers. And there are a host of different policies that you can make use of, but it's a really important step that you can have shifted left before it even ends up in your cluster. So something that I'm also trying to advocate for more of is shifting things left to the point of your initial developer workflow. A lot of people that work with Kubernetes also make use of a local Kubernetes cluster. So like I said, in our case, we were making use of Amazon EKS, but a number of us on the team were also running local clusters, whether they were spinning up a Kubernetes cluster using Vagrant boxes, or if you're going to make use of Minikube, etc. But there are some really cool tools out there, and one that is one of my favorite ones, and maybe I'm a little biased over here, is Rancher Desktop because of how simple it is. And I think it's especially useful for developers who do want to have all the cluster configuration complexities abstracted away. It makes life a lot easier. So it spins up your cluster for you. It's very easy to manage the version. And so you're interacting with your Kubernetes cluster. But remember, if you put yourself in the shoes of a developer whose job is to focus on application development, like maybe they're dealing with a React.js application or Angular that they're building out, they don't really want to deal with the intricacies of raw manifest files or Helm charts, etc. And so they may not even understand the best practices when it comes to that. But it is a cloud native application. So how do you keep things secure in a context like that? And so in this diagram over here, you'll see that I've rendered the Rancher Desktop icon there for the cluster. But in addition to that, I've also put Datree. And the reason being is Datree also allow for you to essentially have Git hooks so that when you're about to commit code, you can essentially have those hooks in place to check with those same security policies that you have for your Kubernetes resources. And this makes you catch things early on before it even ends up in the Git repository where you might be, which might kick off a pipeline or which might be used for a Git ops strategy. So you can find that, especially for developers, this will be especially useful if they're using, as in addition to that, a tool like Scaffold, which helps with generating the resources. Those resources still have to go through the filter of something like a tree policy enforcement. All right. So another pain point that we dealt with, and yeah, this one was really interesting, was secrets management. We actually had all of our secrets stored in AWS Secrets Manager. To date, that is still my favorite secret solution for centralized management, that is, but there are obviously other tools out there like HashiCorp Vault as well that you can make use of. But the point is, the topic of secrets in Kubernetes is a really important one, and I also find that there are a lot of misconceptions around it. So by default, secrets are not secure. A lot of people sometimes mistake base64 encoding for actual encryption, and it is not. So by default, Kubernetes secrets are one of the means of storing cluster configuration in your cluster. The other approach would obviously be config maps, but as the name implies, secrets is for sensitive data, whether it's passwords, tokens, certificates, SSH keys, you name it. And so your pods can consume these, whether mounting them as volumes or environment variables. However, an easy win is to actually enable encryption at rest for your etcd. But in addition to that, a number of teams actually want to make use of their secrets also in a Git ops strategy, but they don't store them in Git repositories for this very reason. If the wrong person gets their hands on your secrets, it's very easy for them to generate the real values just by running a base64 decode demand. And so I do like to share a lot about some of the means or tools that you can use to actually encrypt your secrets. And so Bitnami sealed secrets is one solution that helps with solving this. And sealed secrets essentially has two components to it. You've got your command line tool, which is kubeseal, which essentially allows you to make use of a public key certificate to encrypt your secrets. And then you also have another component, which is the sealed secrets controller, which will actually be running inside of the cluster. And the sealed secrets controller is actually responsible for generating the private key and the public key. So this might be taking some of you back to your computer science days. I know this is something that we covered when we were covering cryptography and dealing with private and public key encryption. So essentially you have one that is used for encryption, the other is used for decryption. So the sealed secrets controller generates both, and you can download the public key certificate to use that with kubeseal to encrypt your secret, and that will produce what is known as a sealed secret. So that sealed secret is safe, and it's something that people like to say you can share that on Twitter, no one will decrypt it, and it's essentially true because you would need the private key, which is only privy to the sealed secrets controller inside of the cluster. So you deploy your sealed secret, and inside of the cluster, the controller will be able to decrypt that and generate a normal secret. And I think this diagram over here will help paint that picture a little bit better. So as I mentioned, you've got your normal secret, which you're going to encrypt using kubeseal and the public key certificate, which will generate the sealed secret. And that sealed secret can now be stored in your Git repository, and no one will be able to derive the real values from that. And so when you deploy that sealed secret to the Kubernetes cluster, the sealed secrets controller will be able to decrypt it and create a normal secret, and your pods can consume it as per norm. I'm glad a friend of mine mentioned to me is like, but how secure is that private key in the cluster? And that's why, having that broader or big picture perspective on Kubernetes security is so important, because if there's another component that you don't keep safe, then that becomes an entry point for an attacker. And all of a sudden your private key isn't that safe. So you have to consider all the different angles and aspects of this. So you heard me mention that in our context, we were actually dealing with secrets in Secrets Manager. So that brought about the question of, okay, how do we get our secrets that are stored in SM? I'm just going to call it SM because I'm using the word secret a whole lot and it becomes exhausting. So how do we get our secrets from SM and bring them into our Kubernetes cluster and expose them over there? And so we were using the external secrets operator, and this is a cool open source tool that is, I think, primarily maintained by Container Solutions now, which is a consulting company for a cloud native consulting company. And so The external secrets operator is a Kubernetes operator that allows you to integrate with different secrets managers out there, whether it's AWS SM or HashiCorp Vault or Google solution or IBM solution for secrets management, because it really is good to go with a centralized management solution when it comes to managing of secrets. And if you're in a situation that I was in, a lot of organizations actually prefer this kind of approach. But you still want to be able to make use of them in your cluster. And so SO has a couple of different components. I'm just going to focus on the secret store and the external secret component. So the secret store component is has a namespace scope. So there is a cluster secret store as well. And this resource essentially determines how your external secret will be accessed from an authentication perspective. The external secret component is what you'll actually use to define the specific values that you want to fetch from your external secrets manager. And so I have a diagram here that might help paint the picture a little bit better. And so you'll see right at the top there is AWS SM, and I've got a couple of secrets values stored in there. And so my secret store is going to determine the how those values are fetched, and the external secret component is going to deal with what is fetched. Now, you need to understand that the secret store still needs to have specific credentials that it's going to use in order to communicate with AWS Secret Manager. And so you have to create a secret, and inside of that secret, you're going to have your AWS credentials stored in there. And so some of you might already be going, that's a little bit of a gotcha. So that secret now has to be kept secure. And that's one of the reasons I love to talk about encrypting your secrets, whether you use sealed secrets or Mozilla SOPs or Helm secrets, because even in a situation like this, your secret store component still has to communicate with a secret resource, and you want to be able to keep that secure, especially if you're going to have your AWS credentials in there. So make sure that that's a resource that's encrypted. But essentially, once the secret store and the external secret component have done their job, they're just going to expose, they're going to create a new secret with the specific values from your secrets manager. And once again, that can be consumed by the pods. So that might be a lot. I think it is a lot. And there's still a host of other things that I didn't touch on, but I wanted to speak specifically about things that helped us in our journey, as well as things that I've learned since then. And I think that they might prove useful to you. Briefly, I started off with ECS and speaking about the infrastructure around that. And then after that, I touched on EKS, which, are specifically Kubernetes, and just different things that have been helpful to us along the way. So thanks a lot for tuning in. I hope that was helpful. And if you have any questions, please feel free to reach out to me directly as well. My email address is over there, luke.mwila@susa.com, or you can also reach out to me on Twitter at Luke9. And if you want to check out some of my video resources, I do have a YouTube channel, and you can just use my full name to search for me, Lukonde Mwila. But I'm going to hand over back to the team.
I usually like to wake up in the wee hours of the morning to get some work done in my study. By the time the family wakes up, I help my wife with the morning routines. As a software engineer, the dream is to be right there at the bleeding edge. The solutions that we build change industries. My name is Odi Enaholo. I'm a senior software engineer at AWS.
Containers are changing the way that we develop, test, and deploy software, making it faster for us to test and deploy and experiment with these new features and capabilities.
We built AWS App Mesh that makes use of the Envoy sidecar capabilities to now give you a complete view of the network, where you can have one consistent mechanism between the communication for all of the different components that now live in your distributed system.
Today, I'm excited to announce AWS Fargate, which allows you to run containers without having to manage servers or clusters.
Because Fargate does it for us. Fargate helped us win customers.
A new service called the Amazon Elastic Container Service for Kubernetes, ECS. This makes running Kubernetes as a managed service on top of AWS much, much easier.
The Amazon EC2 Container Service. A highly scalable, high-performance container management service.
Moving to containers, if you have not done it, do it. It will simplify your life quite a bit.
Hey, it's Adam and Brent, and we wanted to let you know that if you're looking for more live or on-demand container content, you should subscribe to our YouTube channel.
Head on over to youtube.com/containersfromthecouch and also check out our website at containersfromthecouch.com. Thanks.
Thank you.
Isn't Luke awesome? I just love that everyone in chat is clapping for the presenters, where we would normally, clap for them when they got done. It restores my faith in the internet just a little bit. So thanks to everyone out there for being a great audience. The chat's been really fun to watch and join along with. So thanks to Luke for walking everyone through container security and some of the principles that we all need to keep in mind as we deploy apps to any public platform. The original plan was to have Luke on live for you, like the rest of the sessions, because personally, I love the energy that live sessions bring, even when they're virtual. But unfortunately, the speed of light is decidedly not customer obsessed and didn't care at all that Joe Berg is on the other side of the planet. So special thanks to Luke for rolling with that situation and recording his session early for us. Luke is in the chat, however, so feel free to let him know if you like the session or if you have any follow-up questions. He's yet another example, along with Casey from this morning, of the AWS heroes and the program there. We're really lucky to have him as part of the event today and as part of the Container Heroes environment. Before we go to break, there's one group that I wanted to highlight. I've seen a bunch of great comments in the chat, and I want to say a big thank you from Amazon to Wes and Arthur, our ASL interpreters for today. One of the goals that we have as a company, and certainly as a product team, is to make it as easy as possible for developers to discover and engage with AWS. And that goes across all of the content we create. One of the ways that we try to do that is to make the content accessible to as many people as possible. It's simply a core part of our job. We shouldn't get any praise or credit for doing this. Providing ASL interpreters is really easy to do. And for the people who need it, it's the difference between being able to participate in events like this and having to wait for videos with subtitles to get released. So from all of us on the Amazon and AWS side, thanks to them for being a huge and important part of the event. Okay, so with that, it's time for a quick break. Don't go too far. We'll start again at 12:30 p.m. Pacific with the next one of our sessions, and I hope you'll join us back then.
The first thing I do when I roll out of bed in the morning, begin to say good morning to the team. Software Development Manager is an enabler. We enable our engineers to build, to use creativity, to prototype. My team started this thing of WFO. I have a yuzu tree, which is now dead. I have dill. I think a deer ate it. My name's Ellen Sue. I'm a software development manager at AWS.
Businesses are constantly looking for ways to optimize their usage within cost-effective budgets. With the broadest and deepest selection of compute instances in the cloud, AWS offers Amazon EC2 Spot instances to help you do more for less. Available at up to a 90% discount, Spot instances are spare EC2 capacity. They use the same infrastructure as on-demand instances, but can be reclaimed by EC2 with a 2-minute notification. This makes Spot instances a great fit with Kubernetes, a container orchestration framework. You can limit the impact of Spot interruptions by diversifying your nodes across EC2 instance families. Spot's compatibility with Kubernetes allows Kubernetes Cluster Autoscaler to direct EC2 autoscaling to automatically spin up a new instance when the current instance is being reclaimed. And when an interruption does occur, regardless if you are running self-managed Kubernetes or Kubernetes through AWS's Elastic Kubernetes service, the AWS Node Termination Handler will automatically drain and cordon the instance. Integrating your Kubernetes workloads with Spot instances means accelerating innovation at your workplace. Scale faster, lower your compute costs, and ultimately do more for less with Amazon EC2 Spot instances.
I really like to start my morning going outside on the patio. The morning standard meetings very important for me because I can know what the team is doing. I think my job is mainly creating an effective team to deliver the most value to customers. I really like when I see my reports growing on their career and also when people are excited about the work that they deliver. We have sister teams also in Cupertino, Seattle, and San Francisco. AWS managed to get everybody on the same page, regardless of which team you are. End of day, learning how to play the guitar. That's one of the biggest challenge outside of my work. I'm Helbert Maish, a software development manager at AWS in Vancouver, British Columbia.
Today, more and more people are running their workloads in containers for better resource efficiency, workload portability, and flexibility. That's why AWS created BottleRocket, a Linux-based operating system that is purpose-built to run containers. BottleRocket updates in a single step, and updates can be rolled back if necessary, giving you fewer error rates for OS updates and increased uptime for containerized applications compared to general-purpose operating systems, which update package by package. You can easily automate updates to your operating system by using container orchestration services such as Amazon EKS, helping to reduce your management overhead and ultimately cutting down on your operational costs. And because BottleRocket includes only the essential components needed to run containers, it effectively boosts resource utilization and lowers security risks. By leveraging BottleRocket's open source development model, you can make your own code changes and produce custom builds that support your preferred orchestrators and build tools. You can also submit your changes for inclusion to the AWS BottleRocket builds. AWS provided builds come with 3 years of support, giving you a single point of contact for all your infrastructure support needs, including operating system support. Build with confidence and optimize your container infrastructure today using BottleRocket.
Welcome back, everybody. After that quick break, let's take a look at the agenda for the second half of the day and give you a little bit of an overview of what you've got coming here before we finish up. Next up will be Clarinda and Yiming talking about scaling and production. And then at 1:15 p.m. Pacific time, Nathan's going to walk us through his findings on concurrency, which I hope you all find as fascinating as I did when I first saw it. It's definitely not a one of the normal container presentations, and the information that he was able to pull out is actually pretty interesting and hopefully useful for everyone. And then our final session today will be at 2 p.m. Pacific, and Adam's going to dump all of the toys out of the toy box and let everyone play. And we're going to show you how to use some of the tools on hand that can take your containerized apps to the next level. Finally, after we're done with those 3 sessions, Inbal will come back and close out the show for us. So that sounds like a fun afternoon to me. We'll go ahead and get started. Kick back, jump into chat if you have any questions. The chat has certainly been one of the highlights of this for me. Thank you all for participating as much as you have, and I hope you enjoy. Well, Clarinda, go ahead and take it away for us.
I usually like to wake up in the wee hours of the morning to get some work done in my study. By the time the family wakes up, I help my wife with the morning routines. As a software engineer, the dream is to be right there at the bleeding edge. The solutions that we build change industries. My name is Odi Enaholo. I'm a senior software engineer at AWS.
Containers are changing the way that we develop, test, and deploy software, making it faster for us to test and deploy and experiment with these new features and capabilities.
We built AWS AppMesh that makes use of the Envoy sidecar capabilities to now give you a complete view of the network, where you can have one consistent mechanism between the communication for all of the different components that now live in your distributed system.
Today, I'm excited to announce AWS Fargate, which allows you to run containers without having to manage servers or clusters.
Because Fargate does it for us. Fargate helped us win customers.
A new service called the Amazon Elastic Container Service for Kubernetes, ECS. This makes running Kubernetes as a managed service on top of AWS much, much easier.
The Amazon EC2 Container Service. A highly scalable, high-performance container management service.
Moving to containers, if you have not done it, do it. It will simplify your life quite a bit.
Hey, it's Adam and Brent, and we wanted to let you know that if you're looking for more live or on-demand container content, you should subscribe to our YouTube channel.
Head on over to youtube.com/containersfromthecouch and also check out our website at containersfromthecouch.com. Thanks.
Thank you.
Awesome. Hi, everybody. I'm glad to be here. I'm Clarinda Mascarenas, Senior Worldwide Container Specialist, and I'm here to talk about how you can build and deploy web applications at scale using AppRunner. So in today's agenda, what I will cover is a quick overview of AppRunner and some of our customer reference use cases. Followed by a quick overview in terms of what we've released so far since GA. And most of our session will actually focus on a quick demo on how you can build an end-to-end web application using AppRunner. So first of all, a big shout out. We've almost completed a year since we've GA'd our product. We GA'd last May. So it's been 1 year and 1 anniversary for us for AppRunner. I want to quickly start off with why we've actually built AppRunner. What we've heard from our customers and developers is that they just want to focus on application development. And typically, they find all these different infrastructure layers that they have to learn. First of all, like AWS Fargate, from a compute perspective, they have to run containers. They got to focus on a container orchestrator. Then they got to think about load balancing, and then auto scaling, and then building their code. And what they've told us is all these different infrastructure layers are so complex, and that's a big learning curve. And so what we've done is we've integrated all this for you, all these different layers of the cake, and we've developed something called as AppRunner, which is a highly abstracted, simple experience for you to develop your web applications. Now, when it comes to AppRunner, let's talk first about what the experience is. What we allow you to do is you can either start with your source code, or you can even start with your container registry. And then all you need to do is give a few configuration parameters, and that'll deploy your application. What you get as an output is a web service endpoint that you can use for your clients to invoke and call these applications. I also want to focus on what are the applications that are best suited for running on AppRunner. Typically, your HTTP-based request response applications, those are the ones that are best suited, as well as any long-running application, basically where a single instance of the application can serve multiple requests during its lifetime. Additionally, we highly recommend that, if you have any state that you need to store, you do that in a database or, on a disk. And last but not the least, we also recommend that you keep the background processing to be limited. Now, let's talk about a few success stories that we've seen already with the AppRunner since our launch. So many of you have heard about Wix, the web application development platform. They've had their customers who've had different requirements because of regulations, et cetera, that they want to connect to backends like databases, et cetera, based on their experience as well. And so what Velo by Wix has done is they've deployed an adapter on AppRunner, which allows them and gives them that flexibility to connect to any backend of their choice. Additionally, also Hubble, it's a startup in Japan. What they've done is they wanted to have their legal processing done very easily and release their features to market, time to market very fast. And that's why they've gone ahead and used AppRunner for AI-powered text extraction, additional tooling capabilities that will help their customers to use their product in a more better manner. Last but not the least, again, is class method. What they've done is they have used a simple pattern, which is called front end for back end processing, where they were able to quickly deploy their microservices based architecture for one of their gaming customers on AppRunner, with the no prior infrastructure experience, and again, faster time to market. What I want to also cover is since our launch, since the 1-year launch, I wanted to quickly recap on what are the capabilities that we have actually shipped with AppRunner. And then we're going to see many of these in a live demo that Yiming is going to walk us through. So first of all, we released the VPC support feature. What that does is it allows you to communicate to any applications within the VPC. Let's say your application has service dependencies like talking to a database, like RDS, etc. And this capability gives you that feature to easily connect with security and compliance. Additionally, from an observability perspective, we've integrated with X-Ray. So what that gives you is it gives you better capability to view your application traces, fine-tuning your performance, allowing you to see if there are any issues going on with your application. And also you can see a service diagram into, a quick view into what's exactly deployed on your stack, which Yiming is going to show us in a bit. From a runtimes perspective, as many of you know, when we shipped AppRunner, we shipped with Node and Python as the 2 runtimes that we supported from a source code repository perspective. And now we've also launched Java this year. We are also worked on the compliance. We are ISO certified. And from a developer productivity perspective, we've always focused on making it simple for developer to build their applications. So using AppRunner, you can integrate with JetBrains and VS Code that directly allows you to deploy your applications developed on it in AppRunner. Additionally, we've also done enhancements with the IAM roles that you can use for security in your applications. And we've also allowed you to launch directly from ECR, which is the container registry that we support today. So if you have any of your applications that you've pushed to a container registry like ECR, we directly have a button that allows you to quickly launch from ECR to AppRunner. So hopefully this gave you guys a quick overview on what AppRunner is, what we have done since GA, and what our success stories have been so far. I'm going to now hand it over to Yiming, who is actually going to quickly walk us through an end-to-end application demo. And he'll be focusing on 2 important capabilities. The first 2 that I've mentioned over here, one is the networking capability with VPC support, and the second one is observability, that's X-Ray integration. So over to you, Yiming.
Sure. Thanks, Clarina, for the great talk. Hello, everyone. My name is Yiming Pen. I'm the software engineer at AWS Containers. My main area of focus is containers compute. I'm one of the founding engineers of AWS AppRunner, and most recently technical lead in the AppRunner app experience business domain with a focus on request routing, auto-scaling, observability, and networking. It is my pleasure to be here with Clarina to talk about our session today. So for this part, I will demonstrate this year our 2 new released capabilities for AppRunner, the VPC and X-Ray support, and how we use them together to benefit our customers. The type of the application we're going to use today here as an example is a Node.js Express application, which interacts with the Amazon RDS database hosted in the Amazon VPC private network. The application manages hotel room information in RDS database. The room information can be retrieved and updated through the HTTP GET and POST API calls to the app. The overall architectural components we're going to walk through for this demo, as you can see in the slides, includes a GitHub repository, contains the source code of my web application, an AppRunner service, which will be used to deploy and host my web application, the RDS database, which stores hotel rooms information data, and the private VPC network, which database will be hosted in. It's very simple and straightforward. For simplification purpose, I pre-created a couple resources in my account, which includes the VPC, the subnets, and the security groups so that you can have the communication between your application and the database. Similarly, the IAM role so that your application can talk to RDS database and X-Ray, and the Amazon RDS database, the X-Ray, and the CloudWatch. So with all this setup, we are good to start our demo. So let's create and configure AppRunner service to enable VPC networking. So let me log into my account. And I will go to my AWS AppRunner console and choose the create service. For the repository type, I choose the source code. And for the connect to GitHub, I choose the GitHub repository and corresponding branch for my web application. And in the deployment settings section, it is optional for you to choose automatic deployment. If you update your source code, the app will do the blue-green deployment underneath hood. So if you have any changes, you don't need to redeploy your service. And it will be auto-updated with the changes and managed by AppRunner. So I choose automatic deployment for convenience here. Click Next. Since it is very simple web application, so I just pass the runtime and the build command start command through the console. The build command npm install. Start command npm start. The port is default. And click Next. In the service settings section, so you can give your service any name you want. It is user-defined name for your AppRunner service. Here we call it Hotel App. I will leave the auto scaling and health check by default value. In the security section, in the instance role, I choose the IAM role I pre-created, which with the necessary permissions to talk to RDS database and X-Ray. And in the networking section, you can see here we have two options for our outgoing network traffic. So one it is public access, the other one it is customer VPC. So for the public access mode, is basically you want to talk to any of your application dependencies over the internet. If you don't want to talk through the private VPC, you want to talk to internet, this is the option you want to choose. And the public access mode is default mode available for you. What we recently released is private VPC mode. You can talk to your database in private VPC network. That way, it's not over the internet. You will be more secure and more compliance. Because we want to talk to our RDS database, which is in private VPC network, so I choose back to the console. So I choose the customer VPC. And we are going to create a VPC connector that allows you to connect application to the RDS database. Here is how we're going to go ahead and do that. So you need a VPC connector to provide your application outbound access to the RDS database, which is hosted in private VPC network. I have a pre-created VPC connector here, which is configured with the destination VPC network name and the subnets, security groups. And as we discussed earlier, the demo app will talk to RDS database. So let's go to our pre-created RDS database console. So the hotel app database, this is the one I pre-created for our application. If you can see, in our RDS database networking set configuration, we set the same set of VPC and subnets, which is hosting the RDS database. And also, which is what we put in our VPC connector here. We recommend 3 subnets for high availability consideration. And for security groups, you must ensure the security group associated with the destination resource have proper inbound rules to allow traffic from the VPC connector security group. So that's for the networking section. And you may notice there's another new section called observability. We have recently added the capability for customers to integrate with AWS X-Ray, so that customers can get traces for their application without having to configure a sidecar or agent on the container. It is a turnkey pre-built observability solution we have built for our customers. I will turn on the toggle and talk more about it later on. Now we click Next. We have a quick overview about our configurations for the App Runner service, and click Create and Deploy. And right now, what it does is building and deploy our Node.js application with the configuration we just set. The service creation will take a couple of minutes because we are building the source code from the GitHub and deploy it on the App Runner. Behind the scenes, it will provision the brand new resource and take some time. While we are waiting our service deployment, I would like to use this time to brief walk through our application source code to see what exactly the application API does and how we do for X-ray trace implementation. So if you can see in the slides, we simply use the OpenTelemetry SDK, which is a CNCF open source project focused on observability, if you know. It will automatically trace your application workloads, includes request and response, and will send them to X-ray. As you can see in the application source code, let me open it. Here we go. So as you can see, I opened the source code of the application. Basically, it contains the main function with the 4 key APIs. We call it add, create, index, and room. It connects to RDS database, and which is hotel room information, includes the room number, floor number, and the has view or not. 3 fields. You can create tables, add items, and list the items. To set up OpenTelemetry instrumentation for this application, depend on the specific programming language of your application. You choose the corresponding language, OpenTelemetry SDK. Here we choose Node.js SDK. So OpenTelemetry supports 2 approach instrumentations, the auto instrumentation and the manual instrumentation. I will use manual instrumentation here as an example. If you are interested in auto instrumentation, you can refer to our blog post. And to trace your application, you need to install OpenTelemetry dependencies in your app package. And to send the trace data to X-ray with OpenTelemetry, you need to configure the X-ray ID generator, the X-ray propagator, and the gRPC exporter in the global trace provider. Here I put all of them in single class. And you don't need to change your API code at all. The traces will be generated automatically as long as you have OpenTelemetry dependency injected in place. To summarize the architecture, it will look like this. And if you want to learn more about detail OpenTelemetry instrumentation and how these 2 approaches works, we have 2 blog posts for providing more details on both auto instrumentation and the manual instrumentation approaches, and sample example code as reference. So let's back to the console to see whether it is still deployment. Yeah, it is still running. So right now, I think the behind the scenes is we still provisioning the resources and to build the application code from the GitHub directly and try to run in the service. And you can see here, we already seen there's a default domain URL and the service arm get created and the source link, which is from our hotel app demo Docker.conf. And you can also see there's a real-time status regarding the logs and activities. So let's waiting the service get created. Okay. As you can see, the service is up and running. And we can select the default domain URL, which is give us the access to the application. If you can see, the website is up and running. It means our application is up and running and connecting to Amazon RDS database with VPC networking successfully. And you can see the top bar, there are 3 APIs on the 3 buttons on the website, which is mapping to the 3 key APIs we saw in the source code, which is rooms, add, and create. And let's do some API calls to let application talk to the backend and connect to database through the VPC to see how exactly works. So first, I will click the rooms button. In the backend, it will call the list API and retrieve the hotel room data from the RDS database through the private VPC network. So here you go. As you can see, the room list displayed on the website. I have pre-created couple hotel room information items in the database, which is we can see on the website now. It means the application and the database read communication succeeded and VPC networking works. And now go back to the main page and click the add button. And I can add a new room here by putting the information. So I will put the room number is 401, floor number is 4, have a good view or not? Yes. So I clicked add room. This shows the response code, which means succeeded. And in the backend, the website will call add API and create a new room information item in the RDS database through the private VPC network. And let's refresh this rooms page. Here you go. If you can see in the 10th item, we get a new item get recorded and created, which means in the backend, the website called add API and created new room information in our RDS database through the VPC network. And it also means the application and the database both read and write communication succeeded, and the VPC networking works. And let's go back to our App Runner console. And you may notice there's a new observability tab. And you may notice there's a tracing, which shows on. So this is the new X-ray tracing feature we introduced in our console for monitoring. If you click the view service map, you can see here It is recording what our behaviors just performed, and it's recording all the activities our hotel app runner service doing, and the communications with the hotel app database, which is our RDS database. Let's click the trace node, and you can see it records and traces the app runner service latency, request, and faults. And click the view traces. If you can see here, it is recorded all the operations we just performed. We performed the get from the room list API by clicking the room button, and we get traced, recorded the post API calls, which is create a new room item, and it is through the URL, which is the same URL we have from the app runner service. So, which means the X-ray is actively tracing our app runner service workloads from the downstream and the upstream. So X-ray gives us a very powerful troubleshooting capability. If there's error or unusual latency, here is how we can debug the application through the X-ray. I'm going to mock a faulty request by removing part of required input parameters, which will cause internal error for the app runner. And we can see how X-ray can help dive and tell us the error details easily. If I go back to the application I have, and I clicked add, and I input 401, I will leave the floor number empty, but which is required in our web application. So add room. So I will see there is missing error get printed out on the website. Then let's go back to the CloudWatch console to see whether this error gets traced. If you can see here, the second last trace ID, it is right up showing the error I just sent. And it recorded the operation I put is post API call, and is which is the HTTP method, and it will show more details if you click into the trace ID, and it will give you more information regarding the response code, the duration, and metadata, and the order response details and the input details. So X-ray also provides us a powerful aggregator function, and we can use it to filter and group requests and look into each request detail further. If you can see here, by default, we refine the query by node, which is the two components in our workloads is RDS database and app runner service. And I can choose the HTTP methods with the put, delete, get, post APIs. And I also can choose it is the HTTP status code. In this way, you can easily find out the error codes and the corresponding trace ID, which means mapping to the request and response you made through some faulty operations. And besides that, if you can see, it gives all the performance details regarding the latency, and you can easily understand what's the breakdown and which activity workloads take longer time, and for you to optimize if you want. So that's the demo part for today, and hope these two capabilities will help empower your application and manage your app runner service workloads and ecosystem easily. So I will hand over the screen to Carolina now.
Awesome. Thank you so much, Yiming, for that great demo. So I wanted to let you guys know, if you guys are interested in learning more, we have a lot of resources that we've already published. We have the X-ray integration that Yiming just showcased. We have a video on that. We also have the VPC support demo that you can see live as well. Additionally, we also have blogs that are published. So if you want to dive deeper into the different modes using OpenTelemetry and X-ray integration, as well as VPC networking, please feel free to refer to this. And if you have any feedback in terms of capabilities that you would like to see in AppRunner or want to provide us any feedback, feel free to use our public roadmap, which is available on GitHub, to give us that feedback. So looking forward to hearing from you, and hope you guys had a great demo session on how you can easily build a web application using AppRunner. Thank you so much, everybody.
Thank you.
Today starts making breakfast for the family. Doing my secret toast with an omelette. A solutions architect is like a cloud therapist. You need to earn the customer trust. I'm obsessed with data. We focus on infrastructure challenges so our customer can focus on their business challenges. My name is Yahav Biran, and I'm a solutions architect at AWS.
Our job is very simple: secure, efficient, and then enable the heck out of the hundreds of DevOps teams that we have across T-Mobile. AWS has really played a huge role in our modernizing our infrastructure and ecosystem at T-Mobile.
Today we run like 1 billion requests a day on AWS, just on our container workloads. So we have used EFS infrequent access. EFS is, as the name suggests, it's elastic. So it can scale up and scale down for demand. We don't have to worry about pre-provisioning a storage. Teams are non-container based workloads. They have access, as long as you have like appropriate tags, you have access to go ahead and provision EFS solutions for you. If you need any extra help on it, we talk with those application teams to configure EFS solutions. The second aspect of self-service is in the container workloads. We enable application teams to use AWS EFS automatically in a Kubernetes cluster. You would just need to write a few lines of code and use Kubernetes manifest to just go and provision EFS cluster, and you can use it in the PVCs. Our requirement for FSX was primarily on big data analytics. A lot of these teams use FSX solutions to get the reporting data as quickly as possible. So the real good thing about FSX is like it's fully managed, and the performance is much better compared to our solution what we had. We actually optimized in terms of like 50 to 60% of cost. It was pretty straightforward for us to migrate these solutions into FSX. Many of the things what AWS provides, we just go and just use it because it saves a lot of time, saves a lot of cost in many of the cases, and scalability. And most important is the reliability aspects of it.
We're continuously delivering value to our end customers on a daily basis versus monthly basis. And what that's allowed us to do also is we've been able to go to market in small markets or with a small subset of our population and do A/B testing for our care and retail applications. And what it's really allowed us to do is get a very broad sample size of what's working and what's not working for our frontline and for our customers, and then to iterate on that and quickly get adjustments and different tweaks out to the market very quickly. So a lot of that has been enabled with our kind of cloud native transformation, and a lot of that work is obviously running within AWS as well.
Thank you to both Clarinda and Yiming for that. It's always a happy day when a live demo gets streamed over the interwebs and everything works the way it's supposed to. So let's all celebrate that as a win this afternoon. We got to see some customer perspectives this morning, which was great, but it's also nice to get a hands-on look and be able to see how we would actually log in and use some of the tech here at AWS. I know that VPC networking with AppRunner was by far the most requested feature that we had from customers that use that product, and the response that we've gotten since it went live has been really great to see. Hopefully, seeing that feature used live helps you as customers or prospective customers see the power that it adds to App Runner and how much easier it makes it connecting to the rest of the AWS ecosystem, including, like we saw, making observability so much better and so much easier to use. There were some great questions in chat. Both Clarinda and Yiming are going to be happy to stick around for follow-ups if you need any more information. And the team has been trying to answer questions as they come in. So there's a bunch of great links in there. They've shared some resources and some information to be able to help people out. And we all wanted to give a big shout out to official friend of the program, Brett Langston, for joining in the conversation over there on Twitch. We definitely notice and appreciate it, Brent. Thanks. Next up is Nathan Peck. And this is another presentation where we're going to dive deep into a couple different tech stacks. And he's going to help us see how they handle concurrency and then share for you why that matters so much, or why that matters at all to applications and application developers. So I think we've got everything set up on the back end. Let's go ahead and transition this over to you, Nathan.
Hello, thank you very much for the intro. So today I'm going to be talking about serverless high concurrency containers on AWS. And I want to start out with talking a little bit about the thing that makes me most excited about concurrency and why. Let's see if we can advance the next slide. I'm not figuring out how to do this. Just a second. Sorry, little technical issues. Yeah, well, so let's talk about what is concurrency and why I should care about concurrency. Let's see. So I want to talk first about the first computer that I ever started out with coding on. It was a Tandy 1000. And the thing that was interesting about this one is there was no concurrency whatsoever. If I was running a program on this computer and I want to run a different program, I actually had to stop the computer and start up put a new disk in and actually restart the computer entirely in order for it to start the new program. Now, advance a couple years later, and we have a new thing in concurrency. If we can advance to the next slide. And that is cooperative multitasking. And so this was a way for programs to run together, and basically they had to check to see if there was another program that was ready and waiting for time to execute, and if so, then it would be given time. And so basically programs would cooperate together and it would yield to another program. So now next up, we have preemptive multitasking. So with this phase, we actually had the operating system keeping track of all the programs, and it would go ahead and manually interrupt a program that was running and say, okay, let me give another program that's running in the background time to execute now. Advancing a few years later, we now have multi-core processors. And so we have the capability for a computer to actually run multiple programs at the same time on different cores of the same processor. So concurrency is increasing as we keep on going. Next up, client-server architecture. And so this is where we are today. We have programs that don't only run locally on your local machine. Instead, they communicate over the internet, and you have these huge server clusters of multi-core processors running in the background in the cloud. And so you have multiple programs running across multiple cores. And sometimes if you're typing something into, let's say, a search bar or one of these programs that's a client-server architecture, what you're doing on your computer is actually being supported by hundreds or even thousands of computers in the background. And so what I find super exciting about this is the idea that concurrency is continuing to advance higher and higher and higher. We could go to the next slide. So we see this exponential growth in the amount of concurrency that systems are experiencing, and increasing complexity as a result of handling all this concurrency. So I want to show an example next of some of the top games that are currently being played on the Steam gaming platform. Obviously, we're streaming on this on Twitch. I know a lot of you are gamers, so you may recognize some of these games. But one of the things you'll see is that there are hundreds of thousands of concurrent players at any given time for most of these popular games. And the interesting thing is all of these games have a client-server architecture, and all of them have hundreds of thousands of concurrent users at any given time. So this gives you an idea of just how popular it is when you can build a concurrent application that handles concurrency. So then this comes to a question. If I want to build a concurrent application, how can I build an application that can actually handle my concurrency? How can I go from 0 users to millions of users? And the answer to that is that you need concurrency optimized compute. You need compute that can start out with low concurrency and can grow with you all the way up to high concurrency. If you think about the life cycle of building an application, of building a business, a lot of times you start out searching for product market fit. You're in a situation where you can't actually attract customers yet because what you're building isn't quite good enough. So at that point, what you need is a way to build things easily. You need low operational costs. You need low baseline costs because you're not making a lot of money yet. But then as you reach that product market fit, you build something that people really like. Now you're wildly successful. You have viral adoption. You have more and more people coming to your service and rapid growth. Now the situation changes. You're not necessarily looking for easy development anymore, but what we are looking for is large amounts of compute at the absolute cheapest sustained usage rate that you can reach. You want to be able to optimize to save money. So there's 3 different serverless container technologies that you can use to achieve this. And I'm going to talk today about AWS Lambda, AWS App Runner, and AWS Fargate. So let's start out with AWS Lambda. And what I want everyone to understand about AWS Lambda is that it is your containerized event handling function in the cloud. And here's what that function ends up looking like. You might have this very simple snippet of code, and you just want to run that. But how are you going to run that? So there's different ways to execute the code. And we're going to talk about, we'll show a little diagram of the different ways. One way is via events. So I could be calling the AWS Lambda API manually to invoke this code, or I could be using a service like AWS Amazon Event Bridge to watch for an event on my AWS account or something that happens like uploading a file to an S3 bucket, and I execute this code in response to that event happening. But the other thing that's usually more interesting to people is executing code in response to web requests. So there's 2 sort of traditional ways that had already existed and one brand new one I want to talk about. The 2 traditional ways are application load balancer, which is just a traditional load balancer, which can invoke a Lambda function in response to a request arriving. And then there's AWS Amazon API Gateway, which is very nice because it is a serverless model. I actually get charged, per request as things go. And it'll execute that Lambda function in response to a request arriving to the API gateway. But the new one I want to talk about is really exciting too, is the Lambda function URL, and the idea that now my Lambda function actually has a URL on the internet where I can call and send a request directly to execute it. But now when that happens, when an event arrives, when a web request arrives, what Lambda does is it spins up multiple isolated copies of my code in micro VMs. So here's what you see. You see handler function and 2 copies of the handler function. Each of them is boxed up in its own micro VM. Now, it's important to consider what happens inside of that micro VM with that handler function. So we're going to talk about the AWS Lambda lifecycle now. There are 3 phases to this lifecycle. The first phase is when I want to boot things up. This code hasn't run yet. We're in a situation where we want it to run though. And so what we need to do is download your container image, extract its contents out. So get your code out of the container image and then load it up for execution inside of this isolated micro VM sandbox. Then there's any initialization code. So code that exists outside of the handler function. Maybe I'm connecting to a database or doing something like downloading a file that I need ahead of time. And then the third phase is the actual function invocation. So this is when an event arrives or when a web request arrives. Now it's time to invoke that function code. Now, it's important to understand how these three life cycles play together when we have multiple functions running at a time, because each function is only ever handling one invoke at a time. So here you see a diagram of how that flow works. If I have one request that arrives, two concurrent requests that arrive, or three concurrent requests that arrive. If I have the first request that arrives, it starts booting up a Lambda micro VM. So I have a cold start, and then the function starts to execute. Now, if I have two concurrent requests that arrive, so there's a request that arrives to that first function instance, but now a second request actually arrives while the first request is being processed. What Lambda has to do is it starts up an entirely new copy of the function. So there's another cold start, and then that other second function starts working on that second concurrent request. And so likewise with three concurrent requests. Three concurrent requests equals three Lambda functions instances in parallel with each other. Now, it's important to consider this because it has an effect on the pricing model. So the way the pricing model for Lambda works is actually quite interesting. You pay per millisecond of time for the amount of time that the initialization code runs and the amount of time that the actual function invocation runs. So here, when my function is starting up with the cold start, there's no charge. But then once my code starts running, I'm charged in each millisecond that code continues to run. So the reason why this model works out really well is because extraordinarily cost effective when there are gaps between work to do. So let's say I haven't quite hit that product market fit yet for my application. There's not a huge amount of usage. And so sometimes, my service could go seconds or maybe even minutes without having any request. Periodically a user will come by and use my application, then they'll leave, and then we'll have to wait a while before that next user actually comes on and starts using my application. So in that situation, each time a user comes in to use my application, I pay per millisecond when my code is running. But then when there's a gap in between where nothing is happening, it could be a second, it could be 500 milliseconds, it could be a minute. There's actually no charge because the system is able to scale down to zero. Now, on the other hand, when I do hit product market fit and I have a lot of users using my system, now I have multiple concurrent Lambda functions being invoked, and each one of them is charging concurrently. So I see all those green areas are stacking up. 3 function instances equals 3 charges. And that kind of leads to the next question of what happens when I have a bunch of concurrent Lambda functions, because I've truly reached that viral status. I have a lot of users. And so we'll see in the next diagram, what that looks like when I have a lot of concurrent users. Well, now I have a ton of Lambda function instances that are stacking up and a lot of these concurrent invokes stacking up. So I'm going to take a pause right here and dive a little bit into what's actually happening during one of these concurrent requests, because that has an important effect on how I might choose to use my compute. So let's talk about what an application is actually doing when a request arrives at my service. This is a very typical workflow for a service. When a request arrives, the server works for about 120 milliseconds. The first thing it does is it validates some input payload. Maybe you're saving some JSON to a database, so it validates it. Then it inserts a row into the database and it has to wait for a response from the database. And so that ends up taking about 10 milliseconds. So then when the response comes back, handles it for about 1 millisecond, and then it makes a call to another downstream service, which takes about 100 milliseconds, and then it waits for that, right? And then finally the response comes back. We serialize a response, which goes back to the end user, and that takes about 8 milliseconds. But let's look at what that is actually. When we break it down, we see the application is spending a lot of time waiting. So here we see, if we do the math, 1 millisecond, 1 millisecond, 8 milliseconds, that's actually 10 milliseconds of code executing. And out of that 120 milliseconds, 110 milliseconds of it were spent waiting. And so we realized that IO heavy workloads, a workload where there's a lot of input, a lot of output, a lot of calls to other downstream services like databases, in these type of workloads, more time is actually spent waiting than there is time spent executing CPU instructions. And so when I look back at a system like Lambda and what has a lot of concurrent activity, I start to look at it and I say, this looks a little bit wasteful. Not only am I paying for all these milliseconds, but I have all of these different Lambda functions that are stacked up, and most of them are spending the vast majority of their time just waiting on a downstream call to a database or to another service. So what's the alternative? And that alternative is event loops. Modern application frameworks, they make it possible for you to handle multiple concurrent requests or concurrent events in a single application process. And the way this works is like an endless loop. So in each second of time, think about it as 1,000 milliseconds of time inside that second that the CPU core can do work. So if I have some small pieces of work that take 1 millisecond, 1 millisecond, and 8 milliseconds, I can actually stack those up into each of those 1,000 milliseconds. And any time that I would normally be just waiting on a downstream service, like a database or another service, I can actually grab some more work to do and put another of those, millisecond pieces of work to do back into the 100 milliseconds. And so instead, you end up with a staggered flow. So if we look at how this works out, instead of doing nothing while I'm waiting, I'm instead grabbing another event, like another request, and I'm doing some more work. So here we start that first request where we validate the 1 millisecond payload. And now while we're waiting for the database, instead of just waiting there and doing nothing, instead we can grab another payload to validate. And then, we see these requests, they basically are staggered out within the same process. And that single application process can keep the CPU completely busy by scheduling work to do into each of those 1,000 milliseconds out of every second. So I want to switch now to showing Node.js code for how to do this, because it's actually built into many programming languages. Node.js happens to be the one that I'm most familiar with and most passionate about. But here we have Node.js that's called async and await. And so here we define an asynchronous function, and the calls that happen inside of this function are prepended by this word await. And so we see every time we see that word await, what that is saying is go back to the event loop and break up the flow of this function into smaller functional blocks, which can be executed out of order, and broken out and scheduled into that event loop. And so if you think back to the cooperative multitasking approach that I discussed earlier, there's a lot of similarities there. Basically, the program is saying, I will optionally yield back to the event loop and allow the event loop to do some other work while I'm waiting. And so here's how it ends up working. We have that initial validation, which takes one millisecond. We have the call to await, which takes 10 milliseconds, but that's no longer considered anymore. If I look at the end-to-end function body from top to bottom, what I see is 1 millisecond plus 1 millisecond plus 8 milliseconds equals 10 milliseconds. And so what this means is I can actually execute this function 100 times per second per process. Because that time, that 10 milliseconds and 100 millisecond is now yielding back to the event loop and allowing another function to execute concurrently with this current function. Now, there's definitely advantages to this approach, but there's also some downsides. For one, it's a little bit harder to code this. It's obviously much more challenging to think about code that executes concurrently. But the other challenge is what happens if you have too many requests per second to arrive. So you have a big burst of traffic, lots of users arrive that want to use your system, and they start sending a lot of requests. So what will happen is all those small micro millisecond blocks of code that need to be executed will start to stack up in memory. And as they queue up, the CPU will become so busy that this queue will overflow into memory. And then eventually you'll have your response time on your service skyrocketing up higher and higher as it starts to take multiple seconds for your CPU to catch up and actually start executing the CPU work that has to be done for serving a particular request. But there's a solution. Solution is we can load balance requests across multiple copies of your application process. And so what this does, it basically splits it 50-50 in this case. Half the requests go to one application process with its own event loop, and half of the requests go to another application process that has its own event loop. And so between the two of them, now able to do twice as much work. But this type of load balancing, this type of horizontal scaling is a little bit challenging to do. So we made a service to help with that. A service is called AWS App Runner. The idea behind AWS App Runner is that each copy of your application can be handling multiple concurrent requests, such as with an event loop. But we're going to handle everything else having to do with scaling and load balancing for you. So here's how that works. You see, there's some things that are fully managed by AWS. I've marked those with the word AWS. And there's some things that are managed by you. And they're your responsibility to make sure that those things are working properly. So here we see client code. That's obviously your responsibility. If you're writing a web app or a mobile application that needs to call your service, you're responsible for that code. And likewise, the backend code, the actual server code that runs, is also your responsibility. You need to make sure that you're using the event loop properly. You're writing that asynchronous code. But everything else in between is all fully managed by AWS. So that includes the ingress and load balancing. That includes the micro VM, similar to Lambda. That includes also the scaling, which causes multiple copies of your application container to be scaled out. And so there's a nice diagram that demonstrates how this stack works. So your client code sends requests to an endpoint for the AWS App Runner service. AWS App Runner just generates this endpoint for you. It gives you an address on the internet that you can send traffic to. And behind that address, we're running our own Envoy proxy load balancer. And this Envoy proxy load balancer accepts your requests and keeps track of them. And we have an interesting concept built in, which is called overflow queue, which allows us to limit how many requests get sent to each copy of your application container. Because as I mentioned earlier, one of the challenges with building an event loop process that handles multiple concurrent requests inside of one process is that process can get overloaded and get stacked up with so much work to do that it can't keep up with it anymore. So we've built in the concept of a concurrent request limit per container and the ability to queue up those requests inside of AWS App Runner instead of overwhelming your application. So let me show you how that works when we actually hit that limit. So we reach a point where one of your application containers is running out of concurrency capacity. Maybe you specified that you never want your application process to receive more than 100 concurrent requests. When we see that happening, we'll preemptively launch a new copy of your application container in parallel and start sending up to 100 concurrent requests to that application container as well. But one of the really interesting things is that if you reach a stage where that one is overwhelmed as well, and you never want to scale out more than 2 copies, maybe for example, rather than overwhelming your application process and bringing it down with lots of traffic so that it completely crashes, we start to reject some of the requests and return back a status code of 429 too many requests. So let me show you how that works as the traffic goes up over time. So in this case, we've specified a hard limit of maximum number of containers is 3. And we've also specified a limit for how much concurrent traffic each container it can receive. But what happens is over time, our traffic rises unbounded. It continues to rise up and to the right, which is a good problem to have. But I want to show you how App Runner scales out as this traffic rises. So as we reach a point where App Runner sees that a particular container is about to be overloaded, it goes ahead and starts up a new copy of that container in parallel. And so you can see as that first 2 start, they handle the traffic quite nicely. But I want to highlight one caveat, which is you want to make sure your application starts up quickly. If your application takes a long time to start up, then App Runner may not be able to launch another container fast enough to handle your traffic spike. And so here we see a small red spike there of 429 errors that are returned because that second cold start took a lot longer than the first. And then obviously, because I have a maximum container instances equals 3, we're not able to launch a 4th container. So as traffic overwhelms what those 3 container instances can handle, then any following traffic after that starts to receive a 429 error as well. But it's very nice that App Runner, it can actually protect your traffic, protect your existing traffic when you do have a large spike, because what can often happen is with some systems is that you actually become so overwhelmed with traffic that no one gets a good experience with your application. Everyone is having to wait 30 seconds for a page to load. With App Runner, we ensure that there will always be a certain baseline amount of service that your customers will be able to have. They will get a response back from the system, and any extra traffic will receive an error. So I want to talk a little bit about the pricing model for App Runner too, because it's very fascinating. The pricing model for App Runner is that when a request arrives, you pay for the CPU when the application gets a request. If we could actually go back one slide, forward one, sorry. Yeah, so you pay for a CPU and memory when the application gets a request, but there is a minimum duration of 1 minute that the container is considered to be active. And during that period, you're paying a certain baseline rate for that container based on how much CPU and how much memory you provision for that container. But it doesn't matter how many requests arrive. I could be serving 1 request per second during that minute, or I could be serving 100 requests per second during that minute. I'll be paying the exact same flat rate. Now, if my application goes inactive because there's no traffic, nobody is actually sending any traffic to the application, then we dial things back so you only have to pay for memory. You don't have to pay for the CPU after that minute is up. But then when requests arrive again, the service activates and you go back to paying for CPU and memory. But once again, it's very fascinating because you don't have to pay per request. The number of requests that a container can handle, you're paying a flat rate for it, whether it's a lot of requests or a small number of requests. So here's how that works as I scale up and up over time. So here, going back to that idea of the traffic rising over time, I start out with 1 container, which is activated, and I'm paying for CPU and memory. And then as the traffic rises, App Runner has to start a new container. I'm now paying 2 times the CPU plus memory. But then when the traffic ends, both of those containers can actually deactivate. So they go down to paying for only memory. And if we reach a stage where there is so little traffic that App Runner decides I need to scale down, it'll stop one and I'll actually go down to paying only 1 times for memory. I won't have to pay for CPU at all. And so you can see that App Runner tries to optimize by scaling down to only memory cost when there's no traffic arriving. Now, this model works really well for a lot of workloads. It doesn't work well for all of them, though. So I want to talk about AWS Fargate next as the third serverless option. And with this serverless option, you once again get a serverless container, but this time you're managing the scaling and concurrency a little bit more deeply. So here you see in this diagram, once again, some things are managed by you, some things are managed by AWS. The client code, once again, is still your responsibility. Application code, still your responsibility. This time, though, the micro VM is the only thing that's AWS responsibility. We'll provide the hosting platform, the capacity for running a particular container, but you're going to decide what the scaling rules are that you want to use, and you're going to decide how you want that traffic to actually reach your application through ingress and load balancing. And one of the ways that you can help decide that is by using an orchestrator. So use the orchestrator to configure and manage your deployment onto AWS Fargate. I usually recommend Amazon ECS as the orchestrator to use alongside AWS Fargate. The way it works is developers can tell Amazon ECS, I'd like to run 10 copies of my application, and I want to register those copies into a load balancer, and I want to scale out the number of copies whenever the CPU utilized by the application goes over 80%. And so the flow works that the orchestrator, in this case Amazon ECS, talks to AWS Fargate in order to launch those 10 copies. And AWS Fargate talks back to the orchestrator to tell the orchestrator, Amazon ECS, metrics about the application. And so ECS is able to see when your application is getting overloaded and respond by launching more containers. But once again, you have to decide those rules yourself. You have to decide what metric you want to scale on, what the numbers are that you want to scale to, and you have to provide a few more of those components, such as a load balancer. You have to spin that up yourself and configure it inside of Amazon ECS to create a connection between the load balancer and AWS Fargate. So it's a little bit more work to set up, but it gives you a lot of control. And I want to talk about that control and the idea that AWS Fargate gives you more choices. So with Fargate, you have a choice as to what API you want to use when interacting with Fargate. One API would be Amazon Elastic Container Service. This is the one that I like a lot because it's fully AWS managed. You don't have to pay for it at all. You only have to pay for the Fargate tasks that you launch using Amazon ECS. And then there's also Amazon Elastic Kubernetes Service. So the advantage of this option is that it's open source. And AWS is managing the deployment of this open source software stack. Now, you do have to pay in order to have your own personal deployment of Amazon EKS for connection to your AWS Fargate cluster. So that is something you may want to consider. Now, talking about choices, let's talk about ingress and load balancing. This is another area where you have choices with AWS Fargate. So you could use an application load balancer. This is what we call level 7 for web requests like HTTP. You could use a network load balancer. This is what we call level 4 load balancer, which is for low-level traffic like UDP traffic, maybe some games would use when talking to their game server rather than using HTTP. There's also AWS App Mesh, which is a service mesh that allows you to accept traffic and distribute it directly from the edge to containers inside your cluster. And then there is Amazon API Gateway, which is the serverless ingress, which you pay per request that comes in to the ingress. So you have options here, 4 different options for ingress. Speaking of scaling, I want to talk about the options for scaling. With scaling, there's a variety of different strategies you can use for scaling. There's step scaling, which is basically you define rigorous rules for, I want to add 2 more containers whenever CPU goes over this percentage threshold. I want to remove this many containers when CPU goes below this threshold. There's also target tracking, which is very interesting. It allows you to specify, AWS, I would like you to try to keep my CPU utilization around 80%, and you decide how many containers to add and remove. And so we observe the patterns of your traffic and attempt to closely match and keep your CPU utilization at a specific target. There's also scheduled scaling, which is great for if you want to scale down overnight. Now, AWS Fargate, I do want to talk about the pricing model because it's different. Once again, you saw Lambda pricing model, you saw AppRunner pricing model. Now, AWS Fargate pricing model, AWS Fargate charges based on time without any concept of activity for your particular application. So as soon as my application starts running inside AWS Fargate, I start paying. And I pay until my application stops running inside of AWS Fargate. The reason why this can still be a very interesting model is if I have very high traffic, it's highly likely that this container is going to be serving requests constantly. And it could be serving hundreds of them per second, hundreds of requests per second arriving at this container. And I'm paying a constant rate, which ends up being lower at high scale than paying per request because it all averages out. So the higher my traffic is, the more I would look at this model and say, this might be something where I consider using it as Fargate because I know that this container can handle a couple hundred requests per second, no problem. There are strategies that you can use to lower the cost for AWS Fargate even more. So the first one is being able to fine-tune CPU and memory to match what your application needs. Fargate offers a lot smaller task sizes than most EC2 instances out there. You can go all the way down to a quarter of a CPU and 512 megabytes of memory. So if I do have a really low traffic application, doesn't receive a lot of activity, I can scale it down and start paying less for it by just getting my Fargate task down to the right size. I can also take advantage of the AWS Fargate compute savings plan. So this allows me to commit to a certain amount of spend on AWS Fargate, and in response, I get a flat percentage discount. And then last but not least, this is actually something I recommend for everyone on all of the compute platforms, is consider trying out AWS Graviton 2, which gives you more price performance. So I'm going to be getting faster applications running on faster CPU cores for the same price, meaning that I can serve more requests per second at the same price than I could on a traditional, Intel or AMD based architecture. So definitely something to consider when you're talking about AWS Fargate. So we've seen these three options. We've seen Lambda, we've seen App Runner, we've seen Fargate. How do I know which one is right for my application? So I want to go through some charts to describe the different characteristics, starting with pricing. Now, the pricing for Lambda, App Runner, and Fargate differ, and this may influence how I choose to run my application. So looking back to Lambda, once again, the price per millisecond per invoke based on memory size of function for Lambda. So each of my concurrent invocations that happen, each of my requests that happen is going to be charged separately in parallel with each other per millisecond based on how much memory I had provisioned for that particular function. Now, this differs from App Runner, which charges based on CPU and memory, and App Runner has this concept of not actually scaling down fully to zero, but it will scale down and stop charging you for the CPU while still charging you for the memory. So when I compare these two options, Lambda and App Runner, I may look at it and say, Lambda is going to work really well if I need to scale down to zero completely. Like I have some situations where nobody's going to call my application for a week. So if that happens, I can scale all the way down to zero with AWS Lambda, whereas App Runner will only scale down based on memory. I'm not going to actually, I'll still have that baseline memory charge through that entire week. I won't be paying for CPU, but I will be paying for memory. So that may be a consideration. Now with AWS Fargate, once again, there is no scale down on either CPU or memory. I'm having a constant price for Fargate as long as that task is running. However, when I look at the flat rate for AWS Fargate and the amount of requests per second that an AWS Fargate container can serve, I may look at that and say the price per request is actually much cheaper on AWS Fargate than it is on other options. So potentially, if I have very high traffic, AWS Fargate looks a lot more attractive to me in that scenario. Also important to consider is pricing resolution. So it's not just how the pricing works, but also how closely it matches the spikes in my demand. So with AWS Lambda, the pricing is per millisecond, rounded up to the nearest millisecond. So if I have a really spiky workload that has requests and then it goes a couple seconds without requests and it has requests, a couple seconds without request, AWS Lambda is closely optimizing for that particular scenario. And I'm paying nothing during those seconds in between my milliseconds of execution. However, with App Runner and with Fargate, there's actually a 1 minute minimum time. So as soon as I start running an App Runner container, it's going to charge for 1 minute. As soon as I start running an AWS Fargate container, it's going to charge for 1 minute. And so my duration of execution gets rounded up to the nearest second. So if I have something where I expect it to be up and down very frequently, I'm not going to really get close match to my usage like I would with AWS Lambda. So I look at that and I say, okay, AWS App Runner and Fargate might work better for a scenario where I know the application will be running straight for a couple hours and of high usage, and then they'll go back down to low usage overnight. Versus with AWS Lambda, that's going to work better for an application which has little spikes of activity throughout the day. And I want to have savings during those, potentially 30-second, 1 minute periods in between requests arriving. So now let's talk about web traffic and ingress. Once again, 3 options for serverless compute, 3 different pricing models and complexity models for web traffic and ingress. So let's start with AWS Lambda. There are 2 different ways. You have a choice. You can either choose to use built-in web traffic and ingress built into AWS Lambda, which is the Lambda function URL, or you can choose to manage your own API gateway or application load balancer on the side. Now, if you do that, you have to pay separately for API gateway or application load balancer. but it gives you a little more control. So you have a choice whether you want to have something that's baked into the Lambda pricing model, which is Lambda function URL, no extra cost, or whether you want to pay in order to have a little bit more control. With App Runner, everything is 100% built in. You get an App Runner endpoint for your service. You don't have to pay anything extra. It's included in the App Runner price. You don't even need to manage anything. There's no API gateway. There's no application load balancer. We have an Envoy proxy, but it's all behind the scenes, built in to the fabric of AWS App Runner in a way that you'd never even see that. With AWS Fargate, though, there is no web traffic or ingress built in to the system. You have to provide your own API gateway or application load balancer and pay for that separately. Once again, though, if you're in a situation where you want that control, chances are you would want to run and operate your own API gateway or load balancer anyway. So that may not necessarily be a problem for your particular workload. And let's talk about scaling now. Scaling is, once again, different across these three different platforms. For AWS Lambda, as we discussed earlier, each function instance is only ever serving a single invoke at a time. So Lambda is automatically increasing the number of function instances and decreasing it behind the scenes. I never have to touch that. I never even have to think about it. So there's a certain very attractive aspect to the scaling model. I know that AWS Lambda is going to be able to handle huge spikes of traffic transparently to myself. I don't have to worry about that at all. AWS App Runner goes a little bit further in terms of giving you a little more control, but a little bit more things to think about. So now I actually have to start to think, with my particular container instance, how many concurrent requests do I actually want it to handle? Do I think it can handle 50 concurrent requests at a time, 100, 150? I have to decide what that number is and maybe try a few different variations before I hit the right balance point where App Runner is scaling properly. But once I find that magic number, App Runner is going to be managing the number of container instances automatically behind the scenes, just like Lambda manages the number of function instances automatically behind the scenes. So once again, that traffic and scaling is being handled for me. With AWS Fargate, there is no built-in scaling. I have to decide that myself, what I want my scaling to be. So I implement my own scaling policy, but once again, I can fine-tune that and make that work. The next area I want to talk about is isolation, which is when the application is running, how are different portions of it isolated from each other? So all three of these serverless options have what we call per process isolation, which means that when one copy of my code is running and another copy of my code is running, they're running in completely isolated execution environments where they can't touch each other. So one Lambda function and another Lambda function are separated from each other. One container and another container are separated in App Runner. And AWS Fargate tasks are also separated from each other. However, Lambda is the only serverless platform on this list that has per request isolation. So per request isolation means that one web request will be isolated completely from all the web requests. And so this makes Lambda unique when I have a workload that is a little bit dangerous. So let's say that I'm in a situation where I need to process an arbitrary web page that was passed in or accept a file upload that potentially is malicious, has a virus in it. I'm definitely going to be looking at AWS Lambda more for that because I know that every single one of those things is hard isolated from each other. Versus AWS App Runner and AWS Fargate, all those requests are potentially happening within the same process, which is good for efficiency, but not necessarily the same security policy. So the thing I would like for you to come away from this session thinking about is that there is this range of serverless compute for different needs. So as I said earlier in the talk, developers who want to build big, exciting things, they need a range of concurrency from low concurrency when they're still initially figuring out their idea and attracting new customers, all the way up to high concurrency when they've built something that's truly viral, something that's really popular and it's getting a lot of users, and now they have more complicated problems to solve. So on the serverless spectrum, the way I see it is AWS Fargate gives you more configurability, more control, however, it is more complex. On the other end of the spectrum, you have App Runner and Lambda, which are aiming to be opinionated, so it's a little bit less to configure, but they're also fully managed and simple. And so these these compute on the right-hand side will tend to be a lot easier to get started with if you are, building your startup, building your new idea, and you just want to focus on building your product. You want to focus on building your code. You don't have to think about infrastructure. But as you build a product that it becomes successful and gets a lot of users, then you start to think about having more control and optimizing for the cost of serving lots of concurrent traffic. And that's where AWS Fargate as a serverless option begins to become more and more attractive. So hopefully we come out of the session with a better understanding of that range. I would like to direct some attention to some further resources you can take advantage of. If you want to try out any of the serverless platforms that you've seen on these slides, I have workshops links here for each of them. So ECS, that'll guide you to using to using Fargate. AppRunner will guide you to using AppRunner, obviously. And then this last link will guide you to spinning up some things on Lambda. And so I highly encourage you, if you haven't yet, get hands-on with each of these serverless container platforms, because you're going to hear a lot about them going forward. And it always works best when you've tried it out yourself and you've seen, okay, I see how my application worked in that. I can understand that I would run this application in Lambda and this application in Fargate. And a lot of large companies, they end up using multiple options. They'll use Lambda and Fargate side by side. So I find it truly fascinating to play with these serverless platforms. And I hope that you try out these workshops and try them out yourself. You can also reach out to me on Twitter at Nathan K. Peck if you have any questions or would like to know more about serverless containers on AWS. So thank you very much for taking the time to watch this session today, and good luck in your serverless container journey.
Today starts making breakfast for the family. Doing my secret toast with an omelette. A solutions architect is like a cloud therapist. You need to earn the customer trust. I'm obsessed with data. We focus on infrastructure challenges so our customer can focus on their business challenges. My name is Yahav Viran, and I'm a solutions architect at AWS.
Our job is very simple: secure, efficient, and then enable the heck out of the hundreds of DevOps teams that we have across T-Mobile. AWS has really played a huge role in our modernizing our infrastructure and ecosystem at T-Mobile.
Today we run like 1 billion requests a day on AWS just on our container workloads. So we have used EFS infrequent access. EFS is, as the name suggests, it's elastic. So it can scale up and scale down per demand. We don't have to worry about pre-provisioning a storage. Teams are non-container based workloads. They have access, as long as you have like appropriate tags, you have access to go ahead and provision EFS solutions for you. If you need any extra help on it, we talk with those application teams to configure EFS solutions. The second aspect of self-service is in the container workloads. We enable application teams to use AWS EFS automatically in a Kubernetes cluster. You would just need to write a few lines of code and use Kubernetes manifest to just go and provision EFS cluster, and you can use it in the PVCs. Our requirement for FSX was primarily on big data analytics. A lot of these teams use FSX solutions to get the reporting data as quickly as possible. So the real good thing about FSX is like it's fully managed, and the performance is much better compared to our solution what we had. We actually optimized in terms of like 50 to 60% of cost. It was pretty straightforward for us to migrate these solutions into FSX. Many of the things what AWS provides, we just go and just use it because it saves a lot of time, saves a lot of cost in many of the cases, and scalability. And most important is the reliability aspects of it.
We're continuously delivering value to our end customers on a daily basis versus monthly basis. And what that's allowed us to do also is we've been able to go to market in small markets or with a small subset of our population and do A/B testing for our care and retail applications. And what it's really allowed us to do is get a very broad sample size of what's working and what's not working for our frontline and for our customers, and then to iterate on that and quickly get adjustments and different tweaks out to the market very quickly. So a lot of that has been enabled with our kind of cloud native transformation, and a lot of that work is obviously running within AWS as well.
Thanks for that, Nathan. That was really great. I love when we have the opportunity in events like this to move past the marketing content and really start to dive deep and talk about not just how to do something, which is important. And I think a bunch of the resources that Nathan shared at the end will help those of you who are looking to figure out how to do something, but also why. You know, with the increasing popularity of serverless platforms, the skills needed to handle scale, you know, and particularly to handle it while not connecting a garden hose to your credit card, are something that we are spending a lot of time focusing on, and that we're hearing a lot when we talk to customers. The real benefits of AWS containers isn't in having one inflexible platform that can do anything if you push hard enough, but it's in having multiple ways to be able to solve your specific app challenge or your specific business challenge. Are you trying to solve for cost? Are you trying to solve for scale? Are you trying to solve for performance? The answer to those questions will determine the right answer for your application today, and the change in those answers over time as the application changes, as the business focus changes, will really help determine what that next step is along, along that path that we go. And having a partner who knows how to help you with that and who has the different ways to be able to run those applications that can help with that, I think is critical. So speaking of ways that having options can make a difference to the applications that you're running, it is time to kick off the last session of the day with Adam Keller. Adam's going to dive into some of the tools that live inside that native container ecosystem and show you how they can make a real difference to how your company, how your developers can deploy apps, how they can manage containers, and how AWS can be the glue that binds all of that together. So with that, let's throw it over to Adam. All yours.
Hey there. Okay, so first and foremost, I need to just get these off here. Okay. So there we go. Thank you everybody for joining today. I really love going from Nathan's talk over to mine because, Nathan really talked about choosing the right, tool for the job, but really it's choosing the right platform for the job. And here we're going to segue into choosing the right tool to deploy your services, your containers, your infrastructure, choosing the right tool for the job there. So, this is all about supercharging your containerized applications with the AWS CDK, the AWS Copilot CLI, and Docker Compose. So just a quick slide about me, in case we haven't met before. Nice to meet you. My name is Adam Keller, and I'm a developer advocate on the container service team here at AWS. And I focus specifically on our container services. So I talk a lot about ECS, Amazon ECS, AWS App Runner, as well as the container ecosystem, and really everything that goes into it. The ecosystem is so large, there's so much to talk about. And you can always reach out to me on GitHub or Twitter. My handles are there. I love to chat about all things containers and all things AWS. I've been in the industry for over 10 years. I've worked with containers, serverless technologies. I was a platform architect in a past life. I led DevOps teams. And with that, I was able to be a part of migrations from the data center into AWS, as well as designing and building greenfield new environments in AWS. And these range from Fortune 500 companies to startups. So I've kind of seen the cultures between the different environments and so on. So what I want to focus on today is I want to talk about containers in the real world. So, I think it was earlier, Casey had mentioned, you have the developer who's writing code on their laptop, on their workstation, and they're testing, iterating locally. They may build a Docker image, and everything's working really great. But you're going to get to a point where it's like, okay, now I need to actually have other people test my application and access my application besides me. So we want to talk a little bit about what it takes to get all of those components there and stitching all the pieces together. And then we'll segue into infrastructure as code, and we'll talk about high-level, opinionated, abstracted tooling, as well as tools that require this deep level of knowledge and how to choose when one versus the other, and so on. We'll talk about Amazon ECS, AWS Fargate, as well as AWS App Runner. Although, truth be told, I don't need to do a whole lot with that because everyone else before me did such a great job explaining all of that. And then we're going to dive into the tools. So I have some demos that I'm going to walk through. Just full disclosure, I pre-recorded them. It's really unlike me, but given that I was going to demo 3 tools, the last thing I wanted to do was have one break and spend time trying to figure that out. So if you want to see me, get into it with one of these tools and see things break and troubleshoot in real time, check out containersfromthecouch.com when we do live streams. I love it when things break there because we'll troubleshoot it live and we'll do it live. So let's talk about running containers in the real world. So it all starts with a developer writing their application code, and they decide, I want to package this code as, I want to package this artifact as a Docker image. This is really cool. It's a great way to just bundle my operating system, my dependencies, and my application code all in one place, and I know this is my source of truth. So I build my image, test it locally, things are looking great. Now we get to a point where we've gone beyond just me as the developer writing my code. I need to put this on a server somewhere, and I need that container image to live somewhere. So if other people want to access my application, say it's a dev environment and I want other developers to be able to test against my application. Well, my container has to live somewhere and it has to run somewhere. And if it's exposed, via a certain port, if we need a load balancer, all these things, I need to start thinking about that. But then what happens as more people start to access my container and my code? Well, now I need to start thinking about scaling. So I launch a couple more. So far, things are okay. We're feeling pretty good. But then I need to integrate a load balancer, because when I have to expose a single container on a single host, I now have to start thinking about port mappings. I can't have port collision. And also, I don't want all of the traffic to route to one container. So the application or the load balancer can help route traffic round robin between my containers. That's all great. But we need to figure out how to stitch those things together. And then as we scale, of course, I'm probably going to need more underlying virtual machines, more hardware to support the containers as they scale out. And then that's great. We're running. We've figured it all out. But now what about metrics? What about logs? How am I auto scaling my application in and out as my traffic patterns, scale in and out? I need to think about those things. I need to think about secrets. How am I accessing secrets? I definitely don't want to be storing secret credentials in my container image. That's not a good practice, right? So we need to start thinking about all of these different components and how we can integrate them with our application and with our containers. And this is where the orchestrator comes in. So this is Amazon ECS as an example. There's also Kubernetes, Amazon EKS, and so on. And these are orchestrators. And the job of the orchestrator is to ensure that the desired state that I've defined for my container is going to be met at all times. In addition, its job is to make sure that any of these other components that I need, it's going to help stitch all of those together. So logging and metrics, that's where the orchestrator comes in to help bridge the gap. Otherwise, I'd have to figure these things out on my own. And you can see it's a lot of work and a lot of thought has to go into this. So now, how do we build this? How do we define this? And how do we actually get this out there in the real world? This is where we start talking infrastructure as code. So this term is used a lot. I use it all the time. I use it to death, to be frank, but there's a lot of value in infrastructure as code. And if I were to define it simply, it's infrastructure as code is basically the process of declaring the desired state of your environments or of your resources using a familiar programming language or a domain-specific language. So, infrastructure as code has come a long way over the past few years. It started with, CloudFormation. In the early days, there were, HashiCorp, Terraform. It was very much, you had to know everything that you were building, and you had to define it via whether that was JSON, YAML, or HashiCorp language, HCL. And you're defining all these resources and managing that and maintaining that. But it's grown. Now, infrastructure as code has gone beyond requiring you to be a deep expert in all of the underlying components. And there's opinion built in now. In addition, you can now declare your infrastructure as code using a familiar programming language like Python or TypeScript with tools like the AWS CDK or Pulumi. And as mentioned earlier by Casey, Gaggle did just that. They started with CloudFormation. They wanted to have more control and also leverage the opinion that was built into the CDK. So they migrated from CloudFormation to the AWS CDK to leverage the power of using a programming language, which we'll talk about in just a little bit. So there's many benefits to using infrastructure as code, whether that's security, because everything you're building is defined in that code. And you should store that code in version control. That should be in Git, right? And any change that's proposed to your infrastructure can be tracked through pull requests, commits, and so on. So now, when I talk to enterprise customers, or really anybody, startups that are just getting into it, I always say use Git, track your changes in Git, and then trigger your deployments from Git. There's no longer the need to have change control meetings, change advisory boards, where everyone sits around a list of proposed changes and tries to discuss it. It's there, it's in code. You can see exactly what the intent is, and approvers will approve it, and there it goes. So beyond that, it's just reproducible. To simply put it, you can take that artifact, that code, and redeploy it across multiple AWS accounts, multiple AWS environments. And this way, when you're testing something in a development environment compared to testing it in a production environment, you know that you're going to be testing against a similar environment. I say similar because your secrets are going to be different. The size of your infrastructure may be different. You may leverage spot instances more in dev environments, smaller database sizes, and so on, because obviously the traffic is much different between environments. So that's high level infrastructure as code. And when we're talking about taking our code from just here's my application to production, here's all of the things we need to be thinking about. So this is kind of similar to what I was just talking about earlier, but I don't just have to think about my code. When I have to think about where's my code going to live. So what's that network look like? It has to live in a VPC. If I build a VPC, I need to think about internet gateways, NAT gateways, subnets, routing tables, routes, security groups, load balancers. And then I also need to think about how am I going to orchestrate my container? How am I going to set the desired state? Where am I going to store that container image? Logging, monitoring, metrics, auto scaling. These are all of the things that I need to keep thinking about as I'm building my application. And then once I have this kind of baseline of here's how my application is going to run, here's how I'm going to orchestrate it and monitor and troubleshoot it. Well, now I want to put that into infrastructure, some form of infrastructure as code. And in addition, we want to wrap that into some sort of CICD pipeline. And we want our code to live in version control. And usually, again, that's where we should be triggering our deployments and our automation is when changes are merged to our code base. And then the last thing to mention with that single service is identity and access management. I need to also think from a security perspective. How am I going to take, if I have a container running an ECS and I need it to talk to an Amazon S3 bucket, I need to be thinking about identity and access management and the policies that I need to create and the roles that I need to create. And then I need to attach those to my tasks running in ECS to ensure that we can talk to those resources. Because by default in AWS, it's least privileged security, meaning when you launch that ECS task or that service, it doesn't have access to anything. You have to explicitly grant that access. Now, what happens when we grow and now we have 2 more services that want to come in, 2 more applications that we want to bring in that our main application is going to talk to? Well, now we need to start thinking about service discovery. Do I need a service mesh? And so on. So, and then it's beyond just network communication. There may be queues. There may be event-driven workloads where we want to trigger and launch tasks based off of certain events in EventBridge. So as you can see, when you build an application, there's much more to it than just writing code and saying, this is great. Now I'm going to throw it over the wall, let someone else handle it. It very much is a team effort, and you have to understand all of the pieces that go into the puzzle to make sure that you're successful in your deployments. So now I want to talk about some of the infrastructure as code tools out there. And what you'll see here is I have a nice little line graph. The bottom left represents the required level of knowledge needed to get started. And anything that's towards the bottom left is going to require a deep knowledge in the infrastructure and resources that you're building. So you have to be intimately familiar with what you're building, and you have to be really thoughtful of all of those resources. As I mentioned earlier, if you're building a VPC, it's not just click a button, build a VPC, and you're good. It's build a VPC, route tables, routes, subnets, span across availability zones, and all that. So leading all the way up to the top, which is the more opinionated tools, which have good practices built in and sane defaults. And with those, generally you want to think about how much can I leverage of the defaults, and then when I need to extend beyond the defaults, can I? And we'll talk about that. So with the deep knowledge, it all starts with the AWS CLI and the AWS SDKs. So this is maybe you write a bash script, a PowerShell script that's going to launch some resources, and based on what you need. This is generally not recommended because when you're building at this low of a level, building your environments, even though you are creating your infrastructure and your resources as code, you have to be aware of creating them, any changes that are made to them, you have to code that. And if you're deleting a resource, you have to code that as well. And then all of the dependencies you have to be thinking about. So generally, these tools are great for when you're interacting with AWS resources rather than using them to build and manage your AWS resources in the long term. And as we move up, this is where we have AWS CloudFormation, which is AWS's native infrastructure as code tool. CloudFormation's been around a long time and is a super powerful infrastructure as code tool. So you define your infrastructure as code using JSON or YAML, and you send it to CloudFormation, and CloudFormation will then take those requirements which you've defined, that desired state of your infrastructure, and then build those resources, update the resources, or delete the resources based on what you've defined and what you've changed in your manifest. Same goes with HashiCorp Terraform. Terraform is an open source infrastructure as code tool, also has been around for quite some time, super powerful. And to define your resources with Terraform, you use what's called the HCL, or the HashiCorp language. This is just a domain-specific language that you'll use that essentially defines your infrastructure as code. It's a little bit further up the scale here, and there's a reason for that. Terraform has a large community, open source community. And what folks have done is they've built modules that can be reused that have a lot of the automation built in. So this is why it leans up towards a little more opinionated, more so than, let's say, CloudFormation. And that's because you can reuse modules, and those have the good practices built in and so on. But just note, oftentimes if they're open source, you want to check who wrote the tool and you want to vet it yourself. So you still need to understand all the things you're building. And then as we move up towards the most opinionated, this is where we see the AWS Copilot CLI, Docker Compose, as well as the AWS Cloud Development Kit. Now, The Copilot CLI and Docker Compose are very narrow in focus because they will deploy your containers or your application code to either Amazon ECS or AWS App Runner. So those are the only two AWS services that you would deploy to. With Copilot CLI, Docker Compose would be ECS. And then there's the AWS Cloud Development Kit, which is where you can define your infrastructure as code. So Python, TypeScript, Java, etc. And it has a lot of opinionated constructs built in with sane defaults, which we'll talk about in a little bit. I tend to do this. I feel like I could talk about that right now and not even have to go to my next slides. So I'm not going to do that here. So we're going to continue on, and we're going to now talk about Amazon ECS and AWS Fargate. And I'm going to sprinkle in a little app runner at the end here. So, Nathan had talked about it. Casey earlier and Maish had a great conversation around how Gaggle is using Amazon ECS in production today, running thousands of tasks to support their customers, thousands of containers to support their customers. And let's talk about what Amazon ECS is at a high level. So it's a container orchestrator. One thing I didn't mention earlier, that when I talk about a container orchestrator, I like to equate it to an orchestra. You have your violinists, the cellists. I don't know the term there. My daughter plays cello. I feel like I should know that. And so on. And it's the job of the conductor to make sure everybody's playing on time and that people come, certain instruments come in when they're supposed to and then leave when they're supposed to. So it's very similar with an orchestrator like Amazon ECS. Its job is to make sure that your desired state of your cluster, of your containers, is being met at all times. So Amazon ECS is a fully managed container orchestration platform. And what that means is, when we talk about the container orchestrators, there's the control plane and then there's the worker plane. So speaking to the control plane, that's your conductor. That's who's telling the orchestra how to play and what to do. That's instructing where to run containers, how to run them, and so on. So with Amazon ECS, you don't have to manage the control plane. It's fully managed. And in addition, you don't have to think about upgrades. You don't have to think about patching, when new versions come out, rotating and ensuring that everything's backwards compatible with that new version. You don't have to think about those. It's all fully managed. You just focus on running your containers in your cluster. And you can also leverage AWS Fargate with Amazon ECS, as well as Amazon EKS. But this is a great way to run containers without having to worry about the underlying virtual machines that your containers are running on. And Amazon ECS is deeply integrated with the AWS ecosystem. So it has tight integrations with AWS CloudWatch for logs, metrics, and monitoring, with the network components, with identity and access management, load balancing. All of these pieces integrate very nicely with Amazon ECS. And then lastly, it actually costs nothing to use Amazon ECS itself, the service, the orchestrator. You just pay for any of the resources that you use. So if you're using EC2 instances, Fargate tasks, and so on, those you pay for. Beyond just running serverless containers, you truly can run your containers in Amazon ECS anywhere. And that ranges from the AWS regions to AWS local zones for those workloads where you need to be closer to your customers. This was a big one for gaming customers. They wanted to be closer to the gamers because if you're like me, we're on Twitch here. Maybe we play video games. I play video games. I don't like latency in my video games. It affects me. So you can run your ECS containers in local zones, wavelength for those 5G use cases, in your data center with AWS Outposts, or in your data center with your own virtual machines or your own infrastructure, your own servers, using Amazon ECS anywhere. So there's a lot of options that you can leverage with ECS, and it's really just up to you as to how you want to leverage them. So with AWS Fargate, as I mentioned, this is a serverless compute offering to run your containers on Amazon ECS, and as well as Amazon EKS. And what that means is, traditionally when used to run containers before Fargate came out, a couple years ago. You would have to think about the virtual machines, the hosts that your container is going to run on. You'd have to register them to the cluster. You have to think about patching, securing, and SSH access, and all of these things when managing your cluster. And in addition, you have to think about scaling your underlying hosts out and in to meet the demand of your applications as they scale. With AWS Fargate, you don't have to think about any of that, because the underlying host, that micro VM that Nathan was talking about earlier, is fully managed by AWS. So that means patching, securing of the host, it's all managed by AWS. You don't have to think about it. You just focus on launching your tasks, and you focus on your application code. So ultimately, it's one less thing that you have to worry about when running your code. So I'm not going to dive too much into App Runner, because I think Nathan did a really good job explaining it. But App Runner is kind of the next level up of abstraction when running containers on AWS, because I just need a web service, whether it's an API or a web server. I tell App Runner, here's my code, which is in GitHub, or here's my container image, and everything else in that orange box, I want you to handle. Building my container image, deploying my container image, using blue-green deployments, creating a CICD pipeline, providing the metrics, encryption at rest. Boy, what else auto-scaling. All of these things are all built in AWS App Runner. So all you have to focus on is what concurrency, what level of concurrency do you want to deem as your scaling metric? And whatever that number is, you set that in App Runner, or you can stick with the default, and then you just write your code. That's it. So we'll talk about some of the tools in just a bit, but with the exception of Docker Compose, all of those tools can deploy App Runner services as well. Okay, so now we have to think about, so let's just quick recap. We talked about containerizing. What does it take to get a container to actually run in the real world? This is all cool. What is infrastructure as code? What are some of the tools that I can use to define my infrastructure and deploy my infrastructure as code? But now we need to think about, well, how do I choose which infrastructure as code tool to use in my journey as I start to deploy containers, or in my existing journey, and how do I move to one of these tools? So I'd like to start by asking some questions. First being, how deep is the team? So understanding your organization, but who's going to be building and managing these resources? And how deep is their knowledge in the underlying components and resources that are going to be built? And then what's the best way for that team to declare the desired state of those resources? So a great example here is if you're a development team and you're pretty deep in AWS, you're also writing code, and you write all your code in JavaScript or TypeScript. So you probably want to stick with a familiar language, not saying everyone's like this, but probably you want to stick with JavaScript. So you want to define your infrastructure as code using JavaScript. So it's important to build in a way that's going to empower your team, and that's not going to provide this huge learning curve to your team that's going to take them months to figure out, and then by that time you're ready to move to something else. How hands-on do you want to be? So this really comes down to kind of like the first question is how deep do I want to be in the infrastructure when we build it? And then how quickly do we want to get up and running? Do we have the time to learn and really understand all of these things that we're building? Or do we want to just focus more so on opinionated tools that can get this done for us, so I don't have to be an expert in everything? And then the last one is just extensibility. How much do I need to extend my application or my infrastructure outside of the tool that I'm using? So now that leads to the first time I've ever done this, but I have these nifty little radar charts here, and they're probably really ugly to look at. But my goal with these was to show, based on the tool you choose, there's going to be give and take, no matter what tool you choose. So in this chart, we basically have these 5 parameters that we look at: the infrastructure knowledge required, And everything is with 5 being the most of that. So if it's a 5, that means you have to really, be all in on that. And if it's 0, obviously you need none. So infrastructure knowledge required, programming knowledge required, extensibility, the getting started experience, and how opinionated the tool is. So as we go through each of these tools, we'll show off the radar chart for that tool so you can see what it looks like. And to get started, we're going to jump into the AWS Cloud Development Kit, the CDK. So the AWS CDK it's an open source software development framework to model and provision your cloud application resources using familiar programming languages. So as you can see on the right, and I've mentioned it 100 times, you can define your infrastructure using Python, JavaScript, TypeScript, Java, C#, as well as Go, which I don't know if it's still in preview, but I believe it is. So having the ability to leverage a programming language you're familiar with, but in addition to leverage the tools that you use with that programming language, like your IDEs, your testing frameworks, it gives you a very similar streamlined experience that you don't have to have a huge on-ramp to get started. And my favorite piece here with the AWS CDK is the opinion that's built in through what are called constructs. So these are built through abstractions, and we'll talk through some of these in a bit, but they always start with same defaults, and then you can build on top and extend as needed. So let's talk about what a construct is in the terms of the AWS CDK. So constructs are the basic building blocks of AWS CDK applications. So when you think of a construct, think of it as a representation of a cloud component that encapsulates everything that CloudFormation needs to create that component. So, an example would be an S3 bucket, to put it simply. So we have 3 levels of constructs. There's the L1 constructs, which are low level. They map directly to CloudFormation. By the way, the CDK basically takes your code and compiles it to CloudFormation, which it then uses to deploy your infrastructure as code. So those are our L1 resources. So if every service that has CloudFormation support will be supported in the AWS CDK, because automatically when CloudFormation support comes out, the CDK will have that support as well. And then we start to move up. So an L2 construct, these are higher level service constructs. So when you look at like an L2 construct, this does not map directly to CloudFormation. I don't have to know CloudFormation to interact with an L2 construct. But essentially, let's think about like an S3 bucket. An S3 bucket has many parameters. There's resource policies. I want to grant access to buckets and so on. When you start to move to L2 constructs, you can leverage a lot of the opinion and abstraction that's built into the CDK. For example, if you want to grant read access to a bucket, there's a helper method available to you with the L2 constructs called, grant read, for example. So these may consist of one or many resources as well. So it may not just be one resource that's being built with that L2 construct. For example, it could build IAM policies that help connect other components to that resource. And then there's the L3 constructs. So these are your opinionated abstractions. And I'm going to show you an example of how to use an L3 construct with Amazon ECS. But these generally stitch many components together, many resources together on your behalf that follow a common use case. So an example would be a load balanced web service. Well, to build that, you need a load balancer network. If you're doing it in ECS, you need a cluster. You need a task definition, service definition, and so on. So the L3 constructs help to stitch those together. And let's actually look at an example of what an L3 construct would look like. So here you can see I'm using the application load balanced Fargate service constructs. This is an L3 construct, and I'm passing in 3 lines of input to this construct. And what it's doing is it has sane defaults built in. So for example, you don't see me defining port here. That's because the default is for port mapping would be port 80, but I can absolutely change that and extend that if I need to. But these 4 lines of code, or I guess 6 lines total here, generate 829 lines of cloud formation. Because what is it building for me? And this is when we talk about opinionated, this is what we mean. It's creating, because I didn't pass in a network, a VPC, which I could if I wanted to. But in this case, it's going to create a VPC for me with the subnets, the routes, route tables, NAT gateways, internet gateways. It's going to create the load balancer, the security groups to connect from my load balancer to my backend container that's running in a private subnet. It's going to create my Fargate service in Amazon ECS. In this case, we're passing in a cluster, but if I didn't pass in a cluster, it would create a cluster as well. So you can see it's building all of these resources on my behalf, and all I have to do is pass in a few lines of code, and the CDK is going to compile it and deploy it to CloudFormation for me. So when we look at this in our chart, you can see that the CDK definitely requires you to be good in a programming language. You have to be familiar with a programming language, or else it's going to be a steeper hill to climb to learn. And then it does offer an opinionated experience, but you can extend it as needed, as I had mentioned earlier. So you can extend these constructs and build on top of them to get whatever type of resource you actually need, or to build, to your definition as what's needed for your environments. So now we're going to dive into a demo. And as I said, we're going to do this via a video, which again, forgive me. So in this demo, we have basically this is a fast API application written in Python, and it's a Wikipedia service. So this is a front-end API that I'm going to use for all my services. I expose it on port 80. And basically what it does is it will you pass in a search term, and it's going to query Wikipedia for that term and then return it back to you. So what I'm going to do to start is I'm going to actually run a CDK version just to confirm that we're running CDK, and you can see we're on the latest version right now. And then we're going to initialize our CDK application. And I choose to use TypeScript as my language. So what's going to happen is the CDK is going to generate this skeleton project structure for me. So I can get started right away and start defining my resources in code with a simple example built in. So you can see here now, here's my structure. We have our package JSON, our CDK.json, which is basically a way for the CDK to feature flag certain features, as well as reference for any type of additional resources or additional configuration that may be necessary. So we're going to start by modifying our CDK stack.ts file. And what I'm going to do is, by initializing our project, by the way, it installed the CDK dependencies that we needed. And now we're going to just simply import them. And I'm going to import 2 modules, the ECS module, which is loaded with L1 and L2 constructs, and then the ECS patterns module, which is where I can build an L3 construct. So as you can see, I'm using VS Code here, and I'm able to leverage the intelligent IDE, which has auto completion built in, and as well as it links to the documentation. So I can see in my editor what resources are optional, what's not optional, and what I need to do. So as you can see, there's many options here to define your environment. I'm not going to pass in a cluster or a VPC here. I want CDK to give me all the opinion and build everything for me. All I'm going to do is say, here's the memory limit that I see necessary to run my application. I need 1,024 megabytes of RAM, and I'm going to stick with the defaults for everything else. Now, the only other thing I want to pass in that's necessary is my container image. So one of the cool helper methods with the CDK is the from asset method. So I can actually let the CDK build a container image for me by simply saying, here's where my container image definition lives. So here's where my Docker file lives, which is under the Wikipedia app directory. And you figure out how to build it, push it to an ECR repository, and manage all of that. So generally, the way you'd have to do this is a Docker build, right? Docker tag, Docker push, and you'd have to have that repository created and so on. CDK is handling that for me because I don't want to even think about that. So this is it. I have, is that like 10 lines of code here? I've defined my container port as well as the container image that I actually want to build and deploy as my ECS service. That's it. Everything else, the application load balancer, the target groups, security groups, VPC, ECS cluster, that's all going to be built for me. So what I'm going to do is just quickly look at the basically the CDK app definition as well as the CDK stack. So when you think of a CDK app, this is basically your CDK application. So this is all of the resources that I want to deploy to the via the CDK. And I'm going to define those resources in stacks. So I can have multiple stacks that are a part of an application in CDK. And in this example, I just have one. And that's going to be my CDK stack here. So I'm going to start by running a CDK synth, which is going to take my code and compile it to CloudFormation. So in just a moment, we're going to see a whole bunch of YAML pop out. And this is what the CDK just built on my behalf. And as you can see, there's a whole lot of stuff there that it's taken care of for me. And let's actually pipe it to a word count just to see how many lines are actually being generated here. And what you'll see is the CDK actually generated 634 lines of CloudFormation that I didn't have to write myself, all with good practices built in, least privilege built in. So for me, if I'm not an expert, but I want to get started and I want to leverage good practices, I can do that. So then I run a CDK diff, which is going to show me basically anything that's changing, what changes I'm proposing to my environment. So you can see IAM changes, the policies, and it's very specific here as to telling you what's changing. And then all the resources that are being created. Since this is brand new, I don't have to, there's nothing to change. And then we're going to run a CDK deploy. I pass in the require approval never flag because when you create IAM resources or security group changes, it will prompt you yes or no to make those changes. It's going to build my container image. I already have it cached. So, and there were no changes. So it built my container image. It wants to push those container images, that container image to Amazon ECR. And then with the magic of fast forwarding here, we're going to build all of these resources. It does take a couple of minutes, especially on the first time. It's going to take a few minutes because it's building a network, it's building a load balancer, and so on. But you can see I get this feedback here via the CLI, and there we go. Now it has output a load balancer URL for me to use, and you can see it took 279 seconds to get everything deployed. So let's go ahead and curl this endpoint. And if I just check the health endpoint, you can see my application's responding healthy. Now, let's actually send a search term to my application. So remember, in 280 seconds, it deployed my application. And now I'm passing in a term. I'm going to search for Los Angeles. That's where I live. And what this will do is it's going to talk to Wikipedia and then return that data back. So as you can see, in 279 seconds, I got an environment with a network, with a load balancer, containers running, ECS cluster, all of these things all built in. And all I had to do was define that in just a few lines of code. So there's a ton more power here with the CDK, and I urge you to try it out. There's the CDK workshop is a great place to get started if you want to just get hands-on with the CDK, as well as ECS workshop has some great stuff there as well. Okay, now we're going to talk about the Copilot CLI. So let's jump to just defining what it is. So the AWS Copilot CLI is an open source command line interface that makes it easy for developers to build, release, and operate production-ready containerized applications on AWS App Runner or Amazon ECS, leveraging AWS Fargate. So when you think of Copilot and you're interacting with Copilot, it offers a fully guided experience that you don't have to be an expert in programming. Although I guess to know your application, you do have to know something about programming, I guess, if it's your application you're dealing with. But you don't have to use that knowledge here. And it's opinionated and it's guided. So Copilot actually will guide you through the deployment experience by you just answering some simple questions, and then it will take care of the rest. So we like to think in terms of architecture, not infrastructure with Copilot. And what that really means is you're focused on your application and the type of pattern that your application fits into. So we'll talk about those patterns in just a moment, but Copilot comes with out-of-the-box support to build CICD pipelines, which if you've ever done this on your own, it can be a pain to have to build these pipelines and deploy them and figure out how to connect all the resources together. Copilot handles that all for you. And then the day two type stuff. So I want to see metrics, logs for my application. I want to set up auto scaling based on CPU metrics, CPU utilization. Copilot simplifies this so greatly that all you have to do is, if you want to auto scale, you just a simple parameter in your manifest, and you say, here's the percentage of utilization that I want to scale on. And then you can use the Copilot CLI to also leverage some of those really great metrics that you may need. So with Copilot, we have the concept of an application. The application is kind of like the umbrella for where your code runs. And, in your microservice environment, you may have, many services or many containerized services that run under one application. And then you have your environment. So this is often your dev, test, and prod. And then your services, which span across. So if I have these environments, I have a service. A service is just how my code runs. So whether that's a load balance web service, a queue-based service, and so on, those run within your environments. And then jobs as well. And the jobs, think of like a cron, where Copilot actually has a really awesome opinionated scheduled task, basically cron type scheduler to launch containers, and it has built-in retries and all sorts of great stuff. And then you can wrap all this into pipelines. So with just a couple clicks of a button, you follow the instructions as you go through the CLI. Copilot can build all these things for you. And of course, you can actually extend Copilot as needed as well. Copilot has the concept of add-ons. So if you need a database, an S3 bucket, Copilot can help build those with just a few commands. But also, if there's something that Copilot doesn't support, you can bring your own CloudFormation to Copilot, and it will deploy that for you as well. So some of the patterns that Copilot builds on are going to be a load balance web service. So this is your front-end web services that are going to serve traffic, from a load balancer, based on a certain path, whatever that is. Those are going to be your load balance web services. Then you have back-end services. So oftentimes these are going to be services that live in, maybe private subnets, or that I shouldn't say live in private subnets, but that don't serve public traffic. And the way your services communicate with one another in that environment would be through service discovery, which Copilot will stitch together and set up on your behalf. So your front end, usually your load balance web service, may talk to a back end service, and it would be done over service discovery, which Copilot will automatically present via an environment variable to your services. So here's the service discovery endpoint that I need to talk to for my back end services. And then there's worker services based on queues, as well as scheduled jobs, and of course, pipelines to help wrap everything up into CICD. Okay, so I'm going to move a little bit faster here. I think I'm talking a lot. So with the Copilot CLI, it is a very opinionated tool. You don't need the infrastructure knowledge to come in and get started right away. You can extend on it using AWS CloudFormation, and the getting started experience is amazing. So let's actually see what that looks like in a demo. So in this case, we're going to use our same application, and we're going to run a Copilot init. So the Copilot init is going to ask me questions. What do I want to name my application? So it's going to be Copilot demo. Remember, the application is kind of the umbrella of all of my services and environments and so on. And then it gives me the option to choose what type of workload I want to deploy. So in this case, I want to deploy my Wikipedia API front-end service as a load balance web service. And that's it. So in my directory, I have a Docker file. One thing you'll notice here is Copilot, just like the CDK did, is going to actually build my container image for me. And in my Docker file, I'm actually exposing, there's an expose flag in my Docker file on port 8080. Copilot's going to read my Docker file and determine if there's any health checks, what port I want to run on, and so on. And it's automatically going to expose my service on that port. So you can see here all of the things that are being built for you, all in this guided experience. And you can see now it's building my Docker image. Remember, I have not defined a VPC. I have not defined an ECS cluster, created a load balancer. All I said to Copilot was, I want a load balanced web service, and I want that web service to run off of this container image, which is the container image file, the Docker file that lives in the directory that I'm building on right now. So you can see it's building the Docker image, creates a repository in Amazon ECR, pushes the image there, and now it's going to deploy my load balancer. It's going to create a service in ECS to ensure that we meet the desired state, that we're always running n number of tasks, and that's it. So Copilot took care of all of that for me, just with me answering a few simple questions. So what I can do now is I'm actually going to take this URL that it provided me, and again, this is the endpoint the load balancer URL. And I'm going to do the same thing I did with my CDK application. I'm going to query this endpoint. I'm going to look for, I want to query Wikipedia to get info on, Los Angeles as my search term. And then I actually put in the wrong path here. It should be the /summary path. And then what's going to happen is I'll see a response and we will be good. So there you go. So in addition to this, so I have an application up and running, literally can be tested within a matter of minutes. This environment's good to go, ready to test. I can use the Copilot CLI to also check the status of my service. How's the health of my service? How many tasks are running? And give me some details on that. In addition, I can view logs for my service. So you can see when I made that call, that 405 method not allowed. And then I finally made the right call to the summary endpoint. So not only does Copilot give me an opinionated way to deploy my containers to AWS using best practices or good practices, it also gives me the tools to have day two visibility and insight. So I say day two a lot. This is getting access into metrics, logs, and seeing how my application's actually performing. So if I were to do the last command I'll run as a Copilot service show, which shows me across my environments, here are the service discovery endpoints. Here are the routes. Here's the information about your configuration for your service. So you can see there's a lot of power built into this tool, and it can take you a long way. We have, if you go to the Copilot documentation, which is shared in ECS Workshop as well as just on GitHub, the AWS Copilot CLI. You can just read, the manifests, all the different options you can use to extend your service. I went very simple here, but I can configure my service to run as I need based on my required needs. So again, that was just a very simple use case. Okay, so the last tool here I'm going to dive into is Docker Compose. So if you're familiar with Docker Compose, Docker Compose provides a way for developers that are very comfortable with the Docker syntax to coordinate multiple containers in one definition, in one manifest, to define how they're going to connect with one another, how they'll talk to one another, as well as just kind of define, you know, a multi-container application in one manifest. So last year, or I believe it's actually a year or year and a half or so ago, we released, or maybe 2 years ago, we released with Docker the ECS context. So with Docker Compose, you can actually launch your containers to Amazon ECS using a familiar language of your Docker Compose syntax. So this is just an example Docker Compose file where I have my front end image defined and my back end image. I talk about any volumes that I need to define, environment variables, and so on. So, okay. So this is Docker Compose here. I'm going to just quickly run through the demo and then I'll wrap up. The one thing about Docker Compose that is really compelling is you can actually take your, you can run this locally. So I do have to build my container image and store it somewhere, but outside of that, I'm just defining some of my resources that I want to run in my Docker Compose file. And all I have to do is, if I want to test locally, that experience is going to be the same as it is then when I deploy it to ECS. So you can see with Docker Compose, you choose what context you want to run in. I'm going to choose to run in the default context, and that default context is going to be my local Docker desktop. So if I run Docker Compose up locally, what's going to happen is it's going to launch that container, and it's actually going to serve it, and it's ready to serve traffic. So if I were to call localhost here, curl localhost 8080, you can see I'm running my application locally. It's working great, and I'm using the Docker Compose syntax that I'm familiar with. I can also curl that endpoint to see here that, same thing. I think I tried to search for Docker here, but I wasn't able to get a response from Wikipedia there. But again, it's this really provides that local experience, that local development experience, and then transition to running that into ECS is very simple. So I'm just going to fast forward just a little bit here. And what you can see is I'm going to stop. Now, what I want to do is switch my Docker context to ECS. When I switch to ECS, what's going to happen is now Docker, when I say Docker Compose up, is it's going to build an ECS cluster, all of the resources that I need to run my container image in Amazon ECS. So again, I'm doing the same, I'm running the same command, the same syntax defined in my Docker Compose file, but what's happening is behind the scenes, Docker Compose actually built all of these resources in AWS for me. And all I have to do is run a Docker Compose PS. I get the load balancer endpoint, and then I can literally query that endpoint, as you can see here, and I'm getting the same response, same thing I had when I was local. So I'm going to just move on here. Actually, this should be done in just a moment here. So there you go. You can see the same command. So what we were able to do here today is we were able to take 3 different tools, leverage the opinion built into those tools to deploy the same application. And really all it comes down to is the comfort level and what you're looking to do, and what makes the most sense for you and your team and your organization. And I did a couple honorable mentions here of CloudFormation and Terraform. As I mentioned, deep infrastructure knowledge you need to have to leverage these tools, but you can extend them quite a bit, and there's a lot of power in using those tools. So check out containersfromthecouch.com as well as ecsworkshop.com to get started. We have a ton of live streams on Containers from the Couch, as well as recorded videos and all sorts of content to help get you started in your journey with containers on AWS. So I don't think there's time for Q&A today, but I'm going to wrap it here. And I just want to thank everybody for listening to me for however long I talked. And you can always reach out to me on Twitter at RealAdamJKeller. And thanks again so much. Appreciate y'all.
Awesome. Thanks, Adam. I appreciate that we made it to the end of the day. I think timing-wise, we're just about wrapped up. So on behalf of myself, all of the developer advocates, everybody, the army of people on the back end of that who's worked on the event that we have here today. Thank you all. Please enjoy what it is that we've put up there, and we will close out with a message from our GM, and that'll be it for today. Thanks, everybody.
Hello, everyone. I hope that everyone enjoys today's session. And one final thought I wanted to leave everyone with is where we're headed next with containers on AWS. As I mentioned at the beginning, our biggest focus is on improving our customer experience and make their life simpler, your life simpler. Now, I don't want to give dates here, but I wanted to give you kind of a sneak peek into what's coming next, at least on some few big releases that are coming. I'll start with ECS. So if we're talking about ECS, we're talking about scalability and scaling. We're going to put a lot of focus, continue scaling our platform, as well as focusing on making granular deployment, as well as easier networking. So you can think about reinventing networking, especially focusing on kind of layer 7 networking, service mesh, service discovery for ECS. And then with ECS Anywhere, we're going to add Windows support as well as load balancer, and we're really just starting to scratch the surface for ECS Anywhere. So 2023 is going to be an impressive year for ECS Anywhere with all the plans we have. Fargate, which is, we get a lot of feedback that customers really like our ECS serverless offering, and we're going to focus on continue improving scaling as well as support for large task support as well as GPU, so you can think about running your large ML workloads on Fargate. And then finally, AppRunner, we already released the VPC connectivity as well as the X-ray support, but we're also going to add new languages runtime and some additional new use case with the idea, again, is to make your life simpler. So when you're developing a web application, AppRunner is there for you. So thank you. It was a very dense day, a lot of information. I hope you had the chance to hear the session, learn something new, and really thank you for attending today. We're very eager to talk to you about containers and application, as well as understand your needs. So please reach out to us. Everyone who registered for the event today will receive an email with in a few days with links to the recordings. And in the meanwhile, there's a lot of material available out there around AWS containers, but I do encourage you to go to the ecsworkshop.com and look on our demos and see how we make onboarding to containers easy with ECS.